Let's wait for attendees to come. Okay, good morning, everybody. I think people will be slowly coming in. Okay, so this is the last session of this marathon conference, which has been going on over 3 sessions. This is the 4th, one of which was during this night. And, you know, this required quite an effort from our administrative and technical team. And I want to publicly thank them. So let's go on. So this session will have only one live talk. Let me share. So this is a session 4, as you can see here. And the first talk will be the talk which has been recorded in session 3 by Thomas Rosenbaum from Caltech. And then we will go for the after that, we will go for the only live talk. Of course, for the recorded talk, it goes without saying that there are no questions to be asked because the speaker is not present. But for the live talk, we will allow some questions. So without further ado, I think we should now stream the recorded talk by Professor Rosenbaum. Thank you very much, everybody.
Very good. Do you see that?
Yes.
That's good. I don't seem to have mine. Ah, there we go. Very good. So thank you so much for inviting me. It's really a great pleasure to be here. And I hope that my talk will both look backwards and point a bit to the future. What I want to talk about is an experimental realization of the Ising model in transverse field, motivated, as many of us have been, by the hope that you can do optimization problems more quickly or more effectively via tunneling, with applications across a broad spectrum of physical systems. I will concentrate on magnets, and in fact, what I want to do is tell you about the first experimental demonstration of quantum speedup in a quantum annealing versus classical annealing experiment. And this was in the disordered ferromagnet. But these experiments are a little old, and they've motivated a number of different approaches. And I want to tell you about the more recent work in the second strand of the talk, which is to talk about nonlinear dynamics of coherent spin clusters in the more dilute limit, where we have the hope of encoding information. So let me start with some additional motivation. If you haven't seen this quote from Richard Feynman, it's a wonderful one. I'm not happy with all the analysis that go with just the classical theory, because nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And so this attraction of a difficult problem that's meaningful, and also one that then lets your imagination run wild about opportunities has been a powerful impetus to the field. It, of course, led Feynman to talk about what a quantum computer would look like. And here's the process flow chart, if you will. You take some input, you look at some combination of classical or quantum processes, perhaps comparing them. You then crunch the wave function, look at the output, and print out your result. So I'm going to tell you about an experiment that's very similar to this on a physical system. The physical system is a dipolar coupled magnet, lithium, holmium, yttrium, tetrafluoride. I will describe the properties of this material system shortly. But basically, you have an initial wave function, initial state. Say that you're in the paramagnet. You quench down into the ferromagnet, either through a classical annealing or quantum annealing protocol. And then you look at what the final state is, the final state wave function. And you do that through a measurement experimentally of the AC magnetic susceptibility. So this is what the material looks like. They're beautiful single crystals. You can buy them in sizes up to centimeters because they're used as laser rods. When they're used as laser rods, they have a large mixture of rare earths, and then you get a lot of protected levels and all. We're interested in just one rare earth, that is the holmium, which is held in the lithium tetrafluoride matrix. And you can do substitution by yttrium. Yttrium is non-magnetic, and that then allows you to tune the energetics of the system, and in fact, the ground state. So this is a less pretty picture of lithium, holmium, yttrium tetrafluoride, but it shows you the crystal structure. The crystal structure is a body-centered tetragonal system. The red dots, I've just shown you the magnetic sites. That's where the holmium, or substitutionally the yttrium, fits. An important part of this is because of the crystal fields. This is an Ising system. So the spins point up along the C-axis. That's the Ising axis here, along here. And the spins are dipolar coupled. Okay, so it's a long-range interacting system. So if you have a pure system, that is all the sites are occupied by holmium, lithium, holmium tetrafluoride, then it's not obvious from the beginning what the ground state should be because of the dipolar interaction admitting both ferromagnetic and antiferromagnetic interaction. So of course, two dipoles like this on top of each other order ferromagnetically, two dipoles like this order antiferromagnetically. But it was shown many years ago by Ludinger and Tizza that basically the first nearest neighbor, which is here, dominates the ground state. So this is a ferromagnet. The first nearest neighbor coupling is ferromagnetic. Second nearest neighbor is antiferromagnetic. But the problem we will have is we're going to have a mix of ferromagnetic and antiferromagnetic bonds competing. So the Curie temperature of this material is 1.53 Kelvin. It's low because it's dipolar. So if it were an exchange coupled magnet, you'd expect to see something, say, of order 1,000 Kelvin. So as you dilute now, substitutionally replacing the holmium, the dipole concentration, with yttrium, which is non-magnetic, you still wind up with a ferromagnetic state, but you get some glassiness because of this competition between the ferromagnetism and the antiferromagnetism. And the Curie temperature just goes linear. It's a 1/r³ interaction in three-dimensional space. If you go farther down, then the sufficient disorder and the competition between the bonds gives you a spin glass state. And when you go even more dilute, you get into a state where you have short-range correlations, but no ordering. And I'm going to spend today this evening, talking about the glassy ferromagnet, that's the optimization measurement, and then the spin liquid, which is the measurement which talks about disparate spin clusters that can encode information. Okay, so let me talk about a transverse field here and what it does. This is the Ising model and transverse field. So for this system, you have a ground state doublet, right? The energy is the same for all spins pointing up, all spins pointing down. The first excited state is 9.4 Kelvin above. I'll be talking about measurements that are done in the millikelvin regime. So there are essentially no excitations, thermal excitations up to the first excited state. However, if you put on a transverse field, remember I told you that the spins can't follow the transverse field to the Ising axis because of the crystal fields in the material. What it does is it mixes the doublet of the ground state doublet with the first excited state and splits the ground state doublet. And now I have an admixture of spin up and spin down that's proportional to this knob that I have in the laboratory, this transverse field. Another way of talking about this, of course, is that the Hamiltonian, this is just the dipolar coupling Jij, these are Pauli spin matrices, commutes with sigma z until you put on a transverse field. And once it no longer commutes, then of course you get quantum fluctuations that depend on the strength of the transverse field. Okay, so you can see this. So here's an experiment that demonstrates this quantum speed up. What I'm plotting here is the imaginary part of the susceptibility. So this is the dissipation versus log frequency. So this is over 6 decades in frequency. So remember I said we're going to do AC magnetic susceptibility. We twiddle at a certain frequency. We ask what's the response. And so you see here with 0 transverse field, a usual sort of response. This is actually for a spin glass system with a temperature about 30 millikelvin or 40 millikelvin above the spin glass transition temperature. You see a broad spectrum like this. It's about 3 orders of magnitude, almost 3 orders of magnitude, full width, half maximum. If this were a single spin, you would see 1.14 decades, the so-called Debye relaxation. Now, as I put on the transverse field, and this is 8 kilogauss of transverse field, the gamma and the Hamiltonian, which is in Kelvin, goes as the square of the applied transverse field of the lab, you see that the frequency response moves up and up in frequency. So the peak frequency here goes from maybe a little over 10 hertz up to 10 to the 4th or a little over 10 to the 4th hertz. Now, the interesting part of this that you can see of how this is working, and that's really quantum, largely quantum, is if I take these curves now and I scale them on top of each other. So the next graph I'm going to show you is the scale by the peak frequency of each of these, and then the maximum. Okay, so that's this plot here. What you see is that this is the peak frequency being 1. And now on the high side, the fast relaxation, basically they all look the same. But as I change transverse field from 0 kilogauss up to 8, these long time, low frequency tails are pulled in. They're pulled in and cut off because there's tunneling through the free energy surface. Okay, so that's the effect of that. This is the experimental setup. We're going to take the material, we're going to mount it with its Ising axis along here, along the sapphire rod. We're going to have a AC susceptibility measurement with these coils that are wrapped around the crystal. The sapphire rods are for thermal heat sinking. And then we're going to put the transverse field perpendicular to the Ising axis, where we have another set of magnets to compensate for any misalignment of the transverse field. So we can make sure that there's no DC longitudinal field, which would just suppress the response and be uninteresting. Okay, so the experiment goes as follows. This is the phase diagram of the lithium homium yttrium tetrafluoride crystal with 44% of the sites occupied by dipoles. You can see this is the classical transition. This is just 44% of 1.53 Kelvin. You see that as I apply a transverse field, and now I'm putting the transverse field in here in terms of the magnetic field, not gamma, but you can plot it either way. You see that I suppress the transition temperature to lower temperature. And then when I reach a critical value of the transverse field, I kill the ferromagnetism. So this is the quantum phase transition. This is the classical phase transition. We've spent time looking at critical exponents and all, and it's not quite like liquid helium where you can get 7 orders of magnitude, but we can get 5 orders of magnitude in terms of the critical behavior. In any case, what I want to do is I want to compare different cooling protocols. So I'm going to call the blue one here classical in the sense that I'm going to cool down only with temperature, no extrinsic tunneling from the transverse field. And then only at the end, when I get to whatever low temperature I'm at, I'm going to raise the transverse field to a certain level here at point C. Alternatively, I could do the quantum annealing. That is, I can cool down, if you will, with a large transverse field on, so lots of tunneling. And then I'm going to come down and turn off the transverse field and come into the ferromagnetic state. And I'm going to come to the same point C. And my question will be, do I get to the same physical state? And how fast do I get there? And I'm going to do that for a number of different points. I'm going to look just inside the phase boundary. I'm going to look a little deeper. I'm going to look very deep in the phase boundary at 30 millikelvin. And then I'm going to look in the paramagnet for a sanity check. Okay, so that's what you're seeing here. Point A is just inside the phase boundary where I have lots of thermal fluctuations, and you can see there's not much change. What I'm plotting here now is the real part of the susceptibility rather than the imaginary part of the susceptibility, because I know that the ground state here is a divergence of this real part of the susceptibility. This is as a function of frequency again now from 1 hertz up to 10 to the 4th hertz. It doesn't go there immediately. It takes time to diverge because of the competition between the ferromagnetic and anti-ferromagnetic bonds. So it's a little glassy in that sense. As I go a little deeper into the state, then I start seeing, I start seeing a difference between the quantum in red and the classical, but not much. They look basically the same. As I go deep into the ferromagnetic state, what you see is the two curves start separating, and the onset of the behavior, the onset of the response to this AC magnetic field starts occurring at much higher frequencies. And this is the quantum speed up. I'll talk about that in a second. We'll focus on that. And then just to convince you that there's real physics to this, if you go back into the paramagnet, there's no difference between the two, even though there's a large transverse field on it. Okay. So this is the quantum speed up. What you see is that you're getting into a different physical state as characterized by the real part of the susceptibility. That was the crunching at the end of this Feynman process, if you will. You see that this lower state has a much higher susceptibility, so it's approaching the divergence. It doesn't actually diverge because there are Demag factors here because it's not a perfect needle. And the onset occurs at about a factor of 30 times larger in frequency than when I do this classically. And this is so-called F0 that I'm going to come back to. These are the most weakly pinned domain walls when they start moving, okay? Because of course I have a bunch of domains and I want to flip them to get the alignment and the net magnetization and the divergence of the susceptibility as I'm entering into the ferromagnetic state. Okay. Now I've given you a lot of heuristics. I don't know if you can read the caption here. It says it appears to be some kind of wireless technology. So let me tell you about the wires, okay? What's going on microscopically. And the lithium holmium tetrafluoride system is beautiful that way because you really do know all the microscopic parameters. And so here are the numbers, if you will. So this is this F naught, the most weakly pinned domain wall. And I'm looking at it as a function of 1 over T. So on the left here towards 0 is high temperature. To the right is low temperature. Obviously, I'm picking 1 over T, log F naught versus 1 over T, because in the classical limit here, I expect Arrhenius behavior, which is a straight line. And now what I can do is I can look at a series of different transverse fields. Remember, I have a quantum parameter now. So a lot of experiments on magnets, quantum magnets, depend on the fact that you go athermal at the lowest temperatures. There's no longer a thermal temperature dependence. And you say, well, that means I must be quantum. But of course, you could just be thermally decoupled. Here, we have the ability to manifestly put in the quantum mechanics and look at a series of different transverse fields indicated now by gamma. And you know that even though over this whole range, it's flat here, it's athermal, that the phase diagram, the gamma T phase diagram, continues to evolve throughout this region. So you know the system's responding. So this is a real indication of being dominated by a quantum process rather than a thermal process. And so what you can do now is you can take slices as a function of the quantum knob in the different regimes. Okay. And what we do is we then map it just onto a simple particle quantum tunneling model, where now the particle is the domain wall and the barrier is really the bunch of spins that are pointed in the opposite direction. And we just use a WKB approximation. And when we solve for that, we can actually, the solid lines here are a fit to this thermal plus quantum channels, where we assume they just work in parallel. And then we can solve for the mass of the domain wall, basically the number of spins. And we find that roughly 10 spins are tunneling at once. So the quantum speed up comes from the fact that if I have two domains here, the green one's down, separated by an up domain, if I want to now get closer to the ordered ferromagnet, I classically flip each of these spins one at a time. But quantum mechanically, I can get a response on the nanometer scale with roughly 10 spins flipping at once from our fit. So that's the origin then of the quantum speed up here. Now, this led to a number, and this is old work. I know that, and I've learned in this conference already, a lot of more modern work. One of the first simulations here that came out a couple of years after our experiments, where Santaro et al., Roberto Carr's group, with an 80 by 80 disordered 2D Ising model. And you can see here, they did basically a classical number of Monte Carlo steps. This is the ground state energy. You wind up with the classical annealing result compared to the quantum annealing. You see the quantum speed up, although this is a 2D system. You do not see, however, you still see a power law dependence. Yeah. And of course, more recently, experimentally, there have been much more elegant, programmable opportunities for doing quantum annealing. The D-Wave system, probably the most famous out there. I know all of you have seen these kinds of graphs where you have the qubits that are tightly connected within a unit cell with certain sorts of connections to other unit cells. Of course, this is one of the older designs. The new designs have many more connections. But the point I wanted to make is that you can program in the problem. Our system, of course, well, it was 10 to the 23rd spin, so it was certainly macroscopic in that way, but it solved its own problem. It found what its ground state was. It didn't really care what you wanted to tell it, to what problem you wanted to solve. Of course, we have some ability here to do that, but these curves with the usual annealing functions here look very similar to the kind of protocols that I was showing you before. Now, there are questions, of course, of whether these superconducting Josephson junctions, how long their coherence goes over this point, over this time. But I think it's really demonstrates the progress that's been made in the field, which is as much quantum engineering as quantum science. So let me move on now to somewhat more modern work. And the motivation for this is the comparison to this notion of only being able to solve the problem the system wants to solve versus being able to program in the problem that you want to solve. And to do that, we're using the same system, the lithium, holmium, yttrium tetrafluoride system, but in the limit of only a few % of the sites being occupied by spins. And this spin liquid, if you will, is very interesting because it has good collective behavior. Basically, it forms isolated spin clusters that can be labeled by frequency, and I'll show you how. And they're competing ground states, of course, which I won't talk about here, but we've done a fair amount of work on. What I'm interested in telling you about, though, is our work using nonlinear dynamics. And by driving the system nonlinearly, we're able to encode information. We have collective excitations that can have coherence times, which are tens of seconds. And there's extreme sensitivity to what the ground state is. So what do I mean by a spin liquid? I'm going to use it in the sense that there's no long-range order as the temperature goes to 0. The spins are not frozen. The fluctuations persist. And in fact, those fluctuations are quantum in the case of lithium, holmium, yttrium tetrafluoride. Their origin is that if you think of the dipolar interaction, if I have a concentrated sample, then the transverse component of the dipolar interaction, remember the dipolar interaction looks like a butterfly, the transverse component of the dipolar interaction cancels in the concentrated case. So if I have a spin here, its transverse component is canceled by the spin on the other side. However, if I now dilute it, I wind up with many spins that do not have compensation. So I have effectively an internal transverse field of order kilogauss that gives you just by dint of disorder, the quantum fluctuations. And it's not a simple paramagnet because there's short-range correlations in this material. So you get collective behavior. So of course, the notion of spin liquids has been studied. There are many lower dimensional systems which show really profound effects. You can get the freezing prevented by the quantum fluctuations, which is what I'm going to talk about today in terms of lithium, holmium, yttrium tetrafluoride with 4% of the sites occupied. But you also have geometric frustration and, of course, amplification of fluctuations with reduced dimensionality. We've done some work on the gadolinium gallium garnet, which shows similar effects, but I won't show them here today. So what does the spin liquid look like? I showed you the spectral response before of the spin glass. And in a lot of ways, this is the anti-spin glass. So what you're looking at here, and I'll explain what I mean by that. What you're looking at here is the real part of the susceptibility at a series of temperatures, 0.18 Kelvin down to 50 millikelvin, 180 millikelvin to 50 millikelvin. And then on the same plot from 10 to minus 1 hertz to 10 to 3 hertz, the imaginary part of the susceptibility. And these contain the same information. They're related by the Kramers-Kronig relationship. But you can see things a little easier on the imaginary part of the susceptibility. One thing you note is as you go from high temperature to low temperature, the system slows down, it moves to lower frequency. If this were spin glass, what you would see is you would see that this spectrum here, which is about 2 decades wide, so larger than Dubai, telling you there's more than one spin doing anything, it would broaden out. Okay, it would get broader and broader and broader as the spin clusters start to freeze in the spin glass. Here, as you see, it's doing the opposite. The spectrum is narrowing, and I'm going to do the same trick. I'm going to look at the imaginary part of the susceptibility. I'm going to plot these on top of each other, normalizing by the peak frequency and the peak height. Okay, and so what you see here is that those same curves coming on top of each other. And now, as I go from higher temperature, the purple, to the lower temperature, the 50 millikelvin, in fact, it almost looks like a gap opens up. the distribution, the spectrum narrows. In fact, it narrows at the lowest temperatures to a full width half maximum, which is narrower than Debye. So it's no longer a relaxational spectrum, right? You can't have less than one spin participating in this. What it tells you is really you should start thinking about this like two-level systems, okay? And so if you imagine a system, a two-level system, one way to probe it is with pump probe spectroscopy. So if you look, or if you think of an ion, you do that. This is not an optical experiment. This is a magnetic experiment. I want to be clear about that, but it's analogous to pump probe and optical bleaching. We're going to burn holes in the spectrum by exciting these clusters, these two-level systems, which are spin clusters, which are effectively composed of a few hundred spins, from their ground state into their excited state. And so how you do this is you use a small amplitude excitation to measure the equilibrium property, and then you fix a frequency at F naught, and you excite the nonlinear response. And to give you an idea of the kind of energies you're talking about, you're only talking about a Gauss or an Ørsted excitation amplitude. So you're not talking about very much magnetic field, but it's enough to burn a hole. So this is about half a Gauss. You can see the nonlinear susceptibility. This is the imaginary part on the top, the real part on the bottom. What you see is basically the hole in the spectrum. The hole in the spectrum can be fit by a phonoform, which means there's coherent scattering between the two-level system and the continuum. And this is the phonoform. I don't want to go through that. This, of course, was developed for atoms by Ugo Fano, talking about the interference, quantum interference between excitations inside the ion and then full ionization of the atom. And there are two parameters here which I want to point out to you. One is the line width, that's the gamma. The other is the phonoasymmetry parameter Q, small q. Okay. So this is our picture. We have these spin clusters. You can label them by frequency in the sense that if I drive this at different frequencies, I pick out different size spin clusters. And then I can excite them out of their ground state, which gives you the hole because they're no longer responding, okay, when I'm twiddling them with that small field. So I have this excitation spectrum. And they're interacting with other excited clusters, but they're also interacting with non-resonantly excited clusters that are close by. So I have excitations up into the higher state, energy state, which tends to be more fully magnetized, and then various pathways that they can relax. And it's the coherence then and the interference between these pathways that gives you the phono line shape. Okay, so let's look at this resonance and understand how it's developing. What I'm trying to get to is to understand what this state is. What are these nonlinear excitations and how can we tune them? And in fact, can we isolate them from their environment so you might start thinking of them like quantum bits? Okay, so here is at low temperature, 110 millikelvin, the imaginary part of the susceptibility versus delta F, which is now the, it's the difference in frequency between the drive frequency that's exciting them and looking about them. And you see here, you get a nice phono line shape as I increase the temperature, and this goes up to 700 millikelvin. The line shape basically broadens until at the highest temperature, I've effectively melted the clusters. So I've just driven them apart. Their binding energy is such that that's not going to be able to sustain those high temperatures. The line width is gamma, and the phono form is basically Arrhenius. Okay, so I'm just having a thermal excitation process. And then you can see what the phono parameter Q is doing. At low temperatures, basically, it's some mix of these different pathways. As I raise temperature, then I'm exciting more of these clusters. I'm flipping basically antiferromagnetic bonds to ferromagnetic bonds. The clusters start revealing themselves to each other and start interacting. And I wind up at one limit of Q. Q goes from 1 to -1. So I'm getting close to the one of the limits, where it's really the interactions between the clusters themselves that are dominating, and there's not much quantum interference left. Okay, so this tells you something about the system and the energy scales in the system. It's not terribly useful otherwise. However, remember, we have a transverse field, and you can also tune this resonance by applying a transverse field. Remind you of the Hamiltonian here, where this gamma, so I'm sorry, the gamma here is the transverse field, not the line width in the phonoresonance. I apologize, I should have changed that. So here you see a sequence of phonoresonances at a series of transverse fields from 2.5 kilogauss to 5 kilogauss. Now, let me point out a couple of things. One is, if I look at one limit, say the 2.5 kilogauss limit, I have a asymmetry about 0 as I move off from the dry frequency. That tells you Q is in one limit. Remember, it goes from -1 to +1. We call this greater than 0. That's sort of arbitrary. But at the highest transverse field, I've gone to Q less than 0, okay? Because it's now on the other side of 0, the asymmetry. And so somewhere in between 2.5 and 5, I'm basically going to get to Q goes to 0. So I'm shifting the energetics and the coupling of the spin clusters. The phonoparameter Q being 0 is interesting because that's where you basically decouple from your environment. That's what it means. There's no interference between those paths. There's no more response to the external field. Okay, and you can see that happens around 3.5 kilogauss here. The other thing I want to point out is, you remember when we just did temperature, the major effect was to broaden the line shape, right? We were melting it, we were smearing it. You can see here, as you move the transverse field, the line width stays very sharp. So there's no broadening here, there's no thermal effect. So this is purely a quantum mechanical effect. And so this is Q mapped out for a series of transverse fields. I just picked out those demonstration plots to show you the evolution. It effectively seems to go roughly linearly through 0, with 0 at about 3.5 kilogauss. And I discuss this in a little more detail in a second. Okay, so what have we found out in tuning this resonance with the transverse field, the phonoresonance with the transverse field in these isolated spin clusters? The line width stays constant, so as the quantum tunneling rate increases, so that's good. We can deconvolute thermal and quantum effects. I haven't showed you here, but it has a long lifetime. In fact, the quality factor, capital Q, and I'll show you that, is effectively independent of transverse field, is something of the order of 10 to the 5th. So it's the frequency we're driving these things at, which is, say, 100 hertz, versus the millihertz line width of this system. You can see this is now a summary of all that data as a function of transverse field, where you're moving from one side of 0 to the other, and you can see the sharpness of this response. So there's weak coupling to the environment because of this large quality factor. And there's no interference then as Q goes to 0. So if there's no interference, the prediction is then that there should be no dissipation. Now remember, we're measuring the imaginary part of the susceptibility, which is a measurement of the dissipation. So what does the imaginary part look like in the nonlinear regime? Okay, so that's what I'm going to plot here. So here, let me just show you this is the Q factor, the quality factor. Okay, so basically of the resonance, which is of order 100,000. So it's a very sharp resonance. This is the phono Q asymmetry parameter, small q, which I showed you before. And down here, I'm looking at the phase. The phase is the ratio of the imaginary to the real part of the susceptibility. So when the imaginary part of the susceptibility goes to 0, phi goes to 0. And what you see is if you look at the nonlinear response, it varies smoothly. I'm sorry, the linear response varies smoothly. That's the red here. But if you look at the nonlinear response, in fact, the dissipation goes to 0 just where the quality, just where the phono parameter crosses 0. Okay, so the fact that you're decoupling from the world, that these are localized states that can be tunably isolated from their environment, is borne out by the measurements of the global susceptibility. So the hope, of course, is that then one can use these, tune this system, these spin clusters, which are now labeled by frequencies, to decouple from their environment and then excite a multitude of spin clusters of different frequencies and then mix them, which would be the computation. We've not done that yet. Okay, let me note that this actually, you can also tune with pump amplitude. So the pump amplitude, of course, drives the system harder, will flip some spins. We see here also that Q crosses through 0. This is the phono Q. As a function of pump frequency, this is from 0.3 of a Gauss up to roughly 0.6 of a Gauss. Here the line shapes, but note that this is not as clean an experiment. I mean, there's probably interesting physics in this, but it's harder to deconvolute effects because see how narrow or reasonably narrow at 0.3 of a Gauss this response is, and by 0.5 of a Gauss, you've already broadened this out. It's because you're heating it. There's eddy current heating in the material's an insulator, but there's metal all around. So we can work on reducing the thermal mixing, but it's hard. So the transverse field is a much better tuning parameter. Okay, so let me conclude. This is lithium holmium yttrium tetrafluoride. It's an experimental realization of the Ising model in transverse field. You can look in different regimes. I've told you about 2 of them. One is the disordered ferromagnet. And here the quantum annealing gets you to the global ground state much faster. And we can microscopically model this and tell you about the domain wall tunneling in a quantitative fashion. And in the spin liquid, you get these nonlinear excitations that create basically emergent degrees of freedom. They're long-lived, they're otherwise inaccessible. And we're now at the point of seeing if we can manipulate them in a way that would be interesting. I think the quantum dynamics of them is interesting in itself, but whether they can be used for mixing would be, of course, is another interesting question. So here, this is what I always tell my students, stick to it. There's a future in cryogenics. And this work has been done over the years with a number of very talented graduate students, David Bitko, Justin Brooks, Cy Ghosh, Michael Schmidt, Dan Silovich, who's a research professor at Caltech now, and my current student, Chris Tang, Wenhao Wu, who's at Texas A&M, both when I was at UChicago, and I've been at Caltech now for 6 years. And all this work has been done with Gabe Epley at ETH. And I won't give you all the old references. If you're interested, please, you can find them under these guys' names. But this is a more recent reference about the high Q nonlinear dynamics that came out last year. So thank you very much for your attention. I appreciate the opportunity to let you know about this, and I will stop sharing.
Thank you very much, Professor Rosenberg. Very interesting talk. So there's a question from the audience. Let me read it. Thank you for your lecture. Do you think quantum tunneling always exists in this problem setting with connection of quantum fluctuation, or on the special circumstances only quantum tunneling exists? Well,
so I think that once you put on a transverse field, it has two effects. In the pure system, it's the quantum tunneling I was telling you about. It also, this is also the random field Ising model. And so you can, in fact, for small transverse fields, you increase the random field pinning. And for large transverse fields, you then see the tunneling and the quantum speed up in the ground state and the domains. And we've done a number of experiments showing that. There's a Nature paper a little while ago that looks at the competition between the random field effects and the quantum tunneling. In the disordered material, very dilute, there are intrinsic quantum fluctuations or quantum tunneling, as I was saying, because of the dipolar interaction being unbalanced. And so, yes, in that case, there's always quantum tunneling. In the pure case, in the classical, at high temperatures, there's probably very little quantum tunneling. One experiment we're doing now, which is kind of fun, is to look at Barkhausen noise in the ferromagnet with the transverse field. So there's been a lot of work, of course, done on the sorts of Barkhausen effects when you just ramp the field around a hysteresis loop, and then you get avalanche behavior of the domains. But as far as we know, nobody's done that in the quantum limits. So we want to look at what quantum Barkhausen looks like. And there we'll be able also to say a lot about what does the quantum tunneling look like, and what are the parameters that characterize it in both pure and disordered ferromagnets.
Okay, thank you. Any further questions from the audience? Daniel, Professor Leader, please.
Yeah, hi. Thanks for a great talk. And
thanks, Dan.
So you've shown all this remarkable evidence that this material is very quantum, so to speak, weakly coupled to the environment and so on. And it just begs the question of programmability of this material, which you mentioned in the beginning. And of course, it's not naturally a programmable material, but I was wondering if one can play tricks like introducing additional impurities that you'd be able to address, something like what's done in NV centers in diamond or phosphorus on silicon and so on.
Right. Yeah, I mean, it's a great suggestion. And actually, Gabriel's doing more in that regime. So you can imagine in a more dilute limit, putting other rare earths in, addressing them optically, then to affect, say, the holmium spin, and being able to control its state, and then looking at the interaction between the holmium spins, where the accessibility is versus, I don't know, an STM or an optical probe or whatever it might be, to couple with the actual spins you want to interact. So I think there are opportunities that way. I think in the bulk material, it's pretty hard, except if we're hoping, as I mentioned, to, if you will, the self-segregation of these clusters to try to work around the fact that we can't actually address them spatially. We're addressing them in the frequency space, so we can't do it in real space. But I think you're right. There are analogs to impurities in diamonds and so on and so forth. Yeah.
I see.
Yeah, it's a great point.
Thank you. Okay. Any further questions? Well, I myself, I'm Hitotoshi Nishimori from Tokyo Institute of Technology. I was very much impressed by your very early work, 1999, and
it's a while back, isn't
it? You established clearly that quantum effects have an advantage over classical thermal effects, but we theorists are still struggling to establish that theoretically. So in terms of the simple transverse field Ising model, as Professor Daniel Lieder talked yesterday or early this morning, he said that simple transverse field Ising model using adiabatic process may not lead to a good amount of advantage over classical methods. So we still have done your homework in that sense. Do you have any suggestions for theorists or in any other respect?
No, I mean, what I've really enjoyed is the large amount of activity in this field. From what I've seen, I am somewhat pessimistic that one is going to really get breakthroughs. Clearly, you can get speed up, but if it's still power law, or or not much change in the power law, there are going to be limitations to its advantages. But one hopes by crafting, at least from an experimental point of view, crafting different experimental configurations with different drive parameters, that we can understand enough about the microscopics to shed some light on the kinds of model systems that you and other theorists are using. So I'm optimistic about that portion. I have less to say about what a real quantum computer will look like.
Thank you very much.
Thank
so
you.
We are just on time, and we thank all the speakers in this session.
Okay, so so this was the recording of Professor Rosenbaum's talk, and we can now go on with the live talk by Wolfgang Lettner. There we go. Okay, so he's already shared the screen, so ready to go. Parity quantum computing. Thank you very much.
Okay, 1 second. Okay, thank you very much. So in the next half hour, I would like to present what we call now parity quantum computing, which is work that accumulated over the last 5 years. And this is something where we have now tried to really improve and enhance upon our original proposal, which is now called the LHZ architecture. And in our original proposal from 2015, we actually assumed, or the problems that we looked at were already in the QAOA form, which means we were discussing all-to-all problems with pair interactions, and this has actually led to a quadratic overhead and a two-dimensional setup. We've also discussed free-body all-to-all, which has led to a cubic overhead. And this overhead in qubits has something that has been criticized from the beginning, and was something that I have dedicated then in the last 5 years research on. And today I would like actually to present how we can not just reduce this overhead, but also improve upon any other QAOA implementation. Things that have been happening since 2015, which I will not talk about today, have been both on the method and on the implementation side. So on the method side, people have looked at so-called counter-diabatic annealing, and we have then used this for our LHZ architecture, where we've seen that we can gain enormous advantages simply because of the fact that we can make use of single-body counter-diabatic driving. And this is a protocol where we really use diabatic transitions in order to circumvent the adiabatic theorem. Another very promising direction is that of inhomogeneous driving. The reason is that the LHZ model is very much reminiscent of the p-spin model. And this is the reason is that there is ordered four-body terms in it, which actually gives quite an improvement by using inhomogeneous driving. Also, together with Andreas Hartmann, we have proposed a variational scheme for annealing, which actually allows one to update the counter-diabatic terms based on the outcome of individual runs. And this is, I think, an interesting direction, because it allows one to use a trade-off between doing many annealing sweeps very fast or a few annealing sweeps very slow. On the implementation side, there have been remarkable experimental and theoretical progress. There have been proposals for implementations with parametric oscillators, Rydberg atoms, transons, flux qubits, and so on and so on. In this talk, I would like to present a new work which has not been published yet and which accumulated over the last 5 years. So this is actually insights that we have gained over quite some time. And I would like to structure it like this. So first, I want to introduce the generalized model, which will then lead to a compiler for our parity model. And using this, I will then show you how k-body terms can be implemented without additional overhead. And also very important, I will show you how optimization problems with constraints can be implemented. So this means problems that on top of having a cuboform also have, so we completely go away from this quadratic unconstrained problems and we go to higher order constraints problems. And last, I would also like to show you another form of generalization where we go from plaquettes to actually linear compilers, which are then very useful for QAOA applications, where the plaquette compiler is useful for adiabatic protocols. So let me show you a generalization of the LHZ model. And to do this, let me first introduce the LHZ model itself from this perspective. In the LHZ model, what we assume is that we have an initial graph which has n nodes and k edges, and we want then to represent the graph by these k parity spins, which are spins that sit on the edges and represent the parity of the two spins at the end of the edge. And by doing this, we introduce k degrees of freedom, which means we represent originally a problem with n degrees of freedom. This means we have to introduce k minus n plus 1 constraints in order to reduce the space again, such that we can represent the original problem. And these constraints we have constructed from closed loops. Closed loops means that in a closed loop, the number of edge variables and spin variables is the same. And what we found was that the general rule is that on in each closed loop, the number of spin downs must be an even number. And this can be then cast into a free body term and physically restrict the phase space to only the valid space. And for all-to-all model, we have found that there is one particular cycle that allows one to fill out the whole space. And this particular pattern is this one. So we go 1 to the right, 2 to the left, 3 to the right, 2 to the left. Now, this is a very specific choice of closed loops. And I want to show you now that this can be generalized to a large extent. And as an example, I would like to show you this particular graph. Imagine you have this graph and you want to map it to parity variables. So this is obviously not an all-to-all graph, but has less than all-to-all. And if we would map it in the original mapping, what this would mean is that we would actually get 15 qubits, but there is very many links which are missing. So for example, the link 2,5 is missing, which means it simply has it's simply a qubit which has a local field which is 0. And all these gray qubits here have local field 0, which means we actually don't really make use of them. So the question is, can we actually compress this problem? And the answer is yes. And the way we do it is we simply select different closed loops. So closed loops which don't follow this original LHZ construction. And in this case, we can now list all the constraints that we have. So we can take all closed loops and just make a list out of them. So for example, this rectangle here, 2, 6, 2, 3, 3, 5, and 5, 6 would be this one. And so I can take all the loops which have length 4 and 5 and just list them here. And then out of these loops, I can try to construct again LHZ plaquettes. So for example, this one would be, so for example, the top left constraint here would be a 4-body term, which would be exactly this rectangle. And then I have 2 3-body terms and 1 4-body term. And if I count the degrees of freedom, this is actually a valid solution because k minus n plus 1 is the number of constraints that I need. And indeed, I have 9 edges, so k equals 9, 6 qubits, n equals 6, plus 1 is 4. So this means for this particular example, this is a valid solution. And the question is now, can I do this in the most general way? So can I do this compression for each graph? And for this, I would first like to introduce a generalized way to look at these closed loops. The reason why we have taken closed loops is the following. Imagine you have your graph, which is represented by these 2-body terms, and now you take out a closed loop of these edge variables. The edge variables are simply products of the 2 spins at the end. So for example, the edge 2, 6 would be simply the product sigma C2 times sigma C6, and so on. Now this means in my LHZ construction, where I have these 4-body terms then, I can actually write out these 4-body terms and they become 8-body terms. So this means if I plug in these new variables into this 4-body term, multiply everything out, this product always becomes an 8-body term. And because now each index occurs twice, so for example, 2, 6, all the indices occur twice. So this is the reason for the closed loop, because each index always occurs twice on each edge. This means this product always gives +1, and that's why it's a valid constraint. So because this must be +1, this makes it a valid constraint. However, I can now reformulate this. I can say, well, instead of looking at closed loops, I can simply say, well, I take any quadruple of pairs, and I just say that each logical index has to appear with an even frequency. So this is, for normal graphs, this is just a reformulation of a closed loop. However, for higher order terms, this allows us to construct constraints out of mixed terms. So imagine we have this Hamiltonian now, so which contains of 2-body terms and 3-body terms. And I've indicated this here. The 2-body terms are the lines, and the 3-body terms I've indicated by these rectangles. So in this case, I can say now, well, with this new definition of a closed loop, I just say, well, each of the indices has to occur with an even frequency. And for example, if I look now at the number of ones that I have in this cycle, there is 1 here and 1 here, so I have 2 ones. And I can do this for every index, and I find that this is a perfectly legal construction. So this means this generalized definition holds now for any k-body terms, which means that the qubits can represent the parity of any k tuple of original spins. And if I look now specifically at this example that I've shown before, I can compare this now to a Kubo construction. If I would decompose this into a Kubo construction, then in the first step, I would have to decompose the 3-body terms into 2-body terms. So this means I get an overhead, or I get ancillas on the logical level, which is already quite expensive. And then I have to embed this graph into some architecture. With the parity compiler, so this means the compression that you've seen before, plus this k-body definition, we can actually represent this whole problem simply by 6 qubits and 2 constraints. So the whole problem is represented by this graph, which is a considerable enhancement, and I will show in the end some benchmarks for actually larger systems. So how does the compiler work? What our compiler actually does it takes all possible closed loops, so closed loops now in this generalized version, and puts them together like puzzle pieces. So this means we just try to find space-filling arrangements of these closed loops, such that we always get out a square lattice without any missing qubits. The compiler can also introduce auxiliary qubits. So sometimes it's necessary to add qubits which actually don't occur in the original graph, just to make it space filling. And now these auxiliary qubits, keep in mind, these are parity variables, which means they actually represent something like hyper edges in the graph. So we're not adding qubits in the logical model, but we are actually adding edges in the graph. And this then often allows us to compile the problem. And here, maybe that's one slide that I'm really proud about. I would like to show you just a gallery of results of this compiler. So the compiler actually takes as input the graph on the left and gives you as the output the graph on the right. And what you can see is that certain patterns of the original graphs also have some patterns then in these parity variables. So for example, if you look at this one, you get out this very symmetric graph. If you look at this one, it's even more symmetric, and so on and so on. So there seems to be a very fundamental correspondence between the graphs and these parity layouts. And again, this also holds for free-body terms, so 4-body terms, 5-body, any k-body terms. So this is also a result of the compiler. Imagine you have this problem Hamiltonian here on the left, which contains a mixture of 2-body and 3-body terms. And this can be cast into extremely simple geometries like this one on the right. And again, each qubit represents a term on the left side, and it's completely independent of how large the k-body term is, so how many products there actually are. They always translate into a single qubit. And just as a side remark, this of course makes sense, because no matter how many terms you multiply in your k-body term, they always split Hilbert space into two pieces, no? Because no matter how many terms there are, you always get a two-level system in the end out of it. It's only -1 or +1. And this means you can represent any k-body term as a single qubit. Okay, so k-body terms are extremely important. The second thing that I want to present now is how to add side conditions. So usually we talk about unconstrained problems. We cast everything into unconstrained problems. But what do we do with side conditions? So this means hard constraints on some variables. So this means our exercise is now, instead of optimizing some Cooper problem, we want to minimize a problem with the condition that, for example, the product sigma 2, sigma 3 equals +1. Now, if we would do this again in a Kubo problem, what this would mean is that we would have to introduce a large energy scale. So this means we would have to introduce a strong bond on sigma 2, sigma 3, and then we would optimize this soft constraint problem. In the parity model, we can actually solve the real constraint problem. And let me show you how this works. Let's take again the example that we had before, and now we have, in addition, the constraint that sigma 2, sigma 3 is +1, which would basically mean that in the Kubo version, we would put a very strong interaction here. Now, in the parity model, we can actually completely circumvent this step and look at it at the following way. Imagine now, instead of taking closed loops of 4, you take closed loops of 5, which include this constraint. So for a typical example would be this one. So we would take basically this form that looks like a house, which has here the constraint in it. Now, if you think again about the constraint construction, what you do is you multiply all the edge variables. So you have a product of 1, 2 times 1, 6, 1 times 5, 6 times 3, 4 times 2, 3. But now 2, 3, we want to enforce that it's +1, which means in our product, this just falls out. And this means we can actually construct now a constraint out of a loop of 5, and we construct actually a constraint which contains only 4 qubits, namely the qubits that are still free. And the constraint is encoded in such a way that it's actually the missing indices in this loop. So this means if I look at all the indices which do not occur with an even frequency in this constraint here, then this is exactly the constraint that I encoded. And this means in the parity model, I can actually remove a qubit by adding a constraint, which totally makes sense, no? Because it removes a degree of freedom, which also means I can remove a qubit. But here I can mathematically make this really happen. It does not remove a constraint, by the way, so the number of constraints must be the same, but I can remove a qubit. And I think that's a fundamentally new way of how we can look at optimization problems. And just to show you a particular example, imagine you have this Hamiltonian here, which contains a large number of constraints, and a large number of terms, plus up to 5 body terms, 4 body terms, 3 body terms, and so on, and a large number of constraints. This would be represented by this graph. This can be cast into this very simple chip. So this can be cast into 52 qubits. And if you would first do this in a Kubo version and then translate it to a chip, this will give you several hundreds of qubits, while here it can be represented by 50. And this is also an outcome of the compiler. As a last point, I would like to mention the line compiler, which is another generalization compared to the original proposal. In the original proposal, we always imagined that the constraints sit on plaquettes, which is for annealing necessary because we have to implement these constraints, which means we want that the couplers sit in the center of 4 qubits. However, if we want to digitally do this, for example, with QAOA, we might want to do this, we have to decompose the 4-body terms anyway into CNOT gates. And by doing so, we actually introduce what we call lines of CNOT gates. So this means a 4-body term is decomposed into 6 CNOT gates, which are performed like on a line. So I can perform them like going clockwise or anti-clockwise or in this C-shaped. And for example, if I make it C-shaped, then actually tilt the graph again, I can make it, for example, like this. Now, and the original idea for this proposal was that this allows you to highly parallelize all the CNOT gates. So by doing this, you can actually make a QAOA run where all the CNOT gates are completely parallelized. However, we can now generalize this with our compiler again. So again, we can just take the number of constraints that we need, find all the constraints that we have, and place them on a square lattice. And so this means we can build, just like the plaquettes, we can build now a chip using this parity transformation with these lines. And these lines now represent CNOT gates that we have to execute. And again, if we look at our example that I've shown now all the time, so what we do now is we first compile the problem, and then we can compile it into CNOT gates. And here again, we have a lot of degrees of freedom, so we can choose how we want to execute these these 3-body terms. And in this example, we then get out 3 steps of parallel CNOT gates that we have to execute. So let me show you now some benchmarks. One is for the annealing. So imagine the benchmark is based on Hamiltonians which contain randomly 2-body, 3-body, and 4-body terms, which we then decompose, and we use 2 compilers. On the left side, we use the D-Wave compiler, which was available by D-Wave. On the bottom side, we show the number of qubits that we need in the parity transformation. And what we see now is first of all, that there is a huge difference between the numbers. So the dots basically represent one problem instance which we've randomly generated. And we already see that, you know, for example, here, if we use around 20 qubits, we have 150 or something like this. So there's approximately a factor of 10 number of qubits. But what we also see is that there seems to be a scaling difference, and this fit here is actually a quadratic fit. So this would indicate that for this certain class of problems, which means we have a lot of four-body terms which are, or three-body terms which are rather sparse, we get a real scaling difference in number of qubits compared to the Kubo transformation. And number of qubits in annealing, of course, leads to exponential difference in the runtime. So this is something that we are currently extremely interested in, and we are currently benchmarking against for many different problem classes. But it seems the ones that have mixed terms of two-body, three-body, and higher order terms. So the more higher order terms, the larger the gain seems to be. The second benchmark that I want to show comes out of a DARPA project that we are currently participating in. So there's this so-called ONISC program running, which aims at showing quantum advantage using QAOA. And our contribution is that in our consortium, we are actually providing the encoding for atomic system. And let us again look at the problem that I've shown before. So we have used this graph. And now if we use our compiler and the QAOA compiler and so on, what we get out is in the end a model with 9 qubits and 20 CNOT gates. If we take the same model and we just compile it, gate model, which uses then swap operations, we actually get 6 qubits and 30 CNOT gates. So this means it seems to be a general rule of thumb that the LHZ compiled version always gives you more qubits but less CNOT gates. And this actually means that if you have no error in your CNOT gates, it's always better to do the standard CNOT gate, the standard gate model with swap operations. However, once you introduce errors on the CNOT gates, there is a window where it becomes advantageous to have less CNOT gates and more qubits. And this is taken from a master thesis from Michael Fellner, one of my students. And what we see here is that on the x-axis is the error rate of the CNOT gate, and then the y-axis is the fidelity of a QAOA protocol with 10 QAOA cycles. And what we see is that for 0 errors with the gate model, we always get larger fidelities. However, there is a turning point at some threshold for the error in the CNOT gates where it becomes advantageous to use the LHZ model. And I think this is quite encouraging because we have used here a rather small system where we already assumed that we have almost perfectly fitting gate model. So in this case, we actually only need 2 swap operations to represent the whole graph. So this means we also looked at the same benchmarks that we looked at for the D-Wave compiler, and what we see is, and we used the Qiskit gate optimization. So we used the state-of-the-art optimizers for the standard gate model. And what we see is that the number of CNOT gates using the LHZ is considerably smaller. So there's like factors of 4 in the number of CNOT gates. I want to emphasize again, so there is of course the trade-off that there's more qubits, but because currently in near-term devices, the number of the CNOT gates are by far the operations with the largest errors, it seems that, or I think that this is advantageous to optimize here for the number of CNOT gates and not for the number of qubits. Okay, so as a summary, I've introduced our parity compiler. What the compiler does is it actually takes any k-body term with constraints and lays it out on a two-dimensional grid with 4-body and 3-body terms, which can then be either decomposed into CNOT operations using digital computing, or they can be implemented directly with 4-body couplers for annealing purposes. I think this really makes the step now from QAOA problems or academic problems to real-world problems. Real-world problems usually contain k-body terms and they contain side conditions. I think for both of these challenges, we have a very elegant answer. I consider QAOA as a workaround which introduces a large overhead in qubits, and it introduces additional energy scale, and we can completely circumvent this QAOA transformation and encode a higher order and constraint problems. Actually, the team consists of two teams in this case. One is the research group. So on the left side, this is my research group at the University of Innsbruck. We are growing quite fast, and to the topics that I presented, more or less everybody contributed. So I could actually name everybody here as a contributor to this work. The research group is at the university, and we are currently actually looking for postdocs. So if you're interested, please apply. On the right side is the spin-out company called Parity Quantum Computing. This is our spin-out that actually writes the compiler. And this compiler will be available as a so-called software as a service. So this means everybody who is interested in actually studying our transformation, please also send me an email. The company is started 2000, so actually this year. We are also growing quite fast, and if you're interested in this, also please just send me an email to this address. So with this, I would like to thank you and ask for questions.
Okay, thank you, Wolfgang, for the nice talk. So while we wait for the audience to ask questions, if any, I actually do have one. I understand this is certainly not the bottleneck in the computation, but do you know how, have you studied how difficult the compiling is
yes.
the input side?
So currently it is the bottleneck.
Okay.
So it's not so easy. Actually, I'm very confident that the compilation is NP-hard itself, which I think is also what we expect from the D-Wave compiler, for example. And
from any compiler in general.
Yes, compilers are, yes. However, basically, yeah, as you say, all compilers are hard problems, and usually they don't give you the optimal solution. So in our case, for example, we have the possibility to add ancilla qubits. By adding ancilla qubits, the problem becomes simpler. However, you add qubits. So this means in the end, it will be a trade-off between how long do you want to compile and how little overhead you want to have. Secondly, there is also other knobs that we can turn. First of all, one thing that we observed is that this line compiler, which is particularly interesting for the digital approaches, is much simpler to compile, simply because you have much more degrees of freedom. However, to parallelize the gates becomes then harder because this is more disordered. So there's also a trade-off then between the efficiency of the quantum algorithm and how much time you spend for the calculation. So the short answer is it's very hard, and that's actually why all these people that you see here are working on the compiler itself. It's extremely interesting mathematics, I have to say. So it's really mapping graphs in a very, very interesting way, where basically geometry and graph theory somehow play together. And we are currently making really a lot of progress. I mean, this is a company where we are professionally doing this now, and we are currently still limited. So we could not, for example, compile a 1000 by 1000 qubit system at the moment, and this is where we want to go.
I was saying that this is probably not the bottleneck, because then you still have 1000 qubit system that you have to run. So that's probably that will be the bottleneck eventually.
Yes.
But I understand that now at this point, actually, the compiler is the most difficult things, because as you said, compilers are NPR. So
yes, yeah.
To solve NPR problem.
But you're right. Fortunately, also hardware is currently at the level of a few qubits, so we can grow with the hardware.
So yes, so nobody will notice that the compiler is slow. Okay, very good. So I don't see any other question from the audience. So I will thank you again, and we will go on with the program of the session. Thank you very much.
Thank you.
So the program now has several, in particular, 1, 2, 3, 4 recorded talks. And of course, the recorded talks will not allow for questions, because the speakers are not online. So I will not intervene between the talks. The talks will be broadcasted by our technicians at ICTP. And I will see you again for the closing of the session around 12:15, plus or minus 5 minutes, depending on how much overtime each talk went. Okay, thank you very much. Enjoy the talks, and see you later. Yep. Yes.
Great. Let me put them in full screen mode.
Fantastic. Okay, I will tell you when 25 minutes say are passed, so that maybe we can leave a couple of minutes for question. Okay, bye.
That would be fantastic. Yeah. So thanks to the organizers for inviting me. And I'd like to talk about the exciting next few years in terms of utilizing the devices we have ahead to get more of an insight into quantum algorithms. And sorry, there we go. So we're at a really exciting era where quantum supremacy has been achieved, but not useful quantum supremacy. There's the possibility of an early application to certified random number generation, but that's a very narrow application. And to go to broader things, such as the things that we're primarily interested in here, like optimization of various sorts and sampling and broader algorithms, it will be a while. So what can we do with these still limited devices, but that go far beyond what can be done in a reasonable time on supercomputers? And one is to do hardware investigations and noise, and that's very, very important. But I want to emphasize here the importance of doing algorithmic investigations, and also how these insights into algorithms can feed into the hardware and vice versa. So I'll be concentrating particularly on optimization and sampling for combinatorial optimization problems in machine learning, but there are other areas that are of great interest, particularly simulation of quantum systems. And unfortunately, there just wasn't time to talk about that, though we are starting to do some work on that at NASA, as well as lots of work in the broader community. So one thing I wanted to emphasize on the optimization and sampling side was that there are diverse optimization goals. You may be looking for exact optimization with guarantees. You may be looking for approximate optimization with guarantees that, for example, you're within a ratio of the exact ground state. You may just be looking for good heuristics without guarantees, but that generally do well. And you may be looking for fair sampling where you can get a variety of solutions, either in the exact or the approximate case. If, for example, you have uncertainty in your ultimate cost function or the circumstances under which your solutions will be deployed. And then there are various sampling goals, such as sampling from a thermal distribution. And a lot of what I will say can apply to all of these, but I don't want to, the more subtle aspects of these are very, very important when we're doing comparisons between algorithms, both between quantum algorithms of various sorts and also between quantum and classical algorithms. I want to really emphasize where we currently are on quantum algorithms. A lot of the hype and press coverage suggests that if we just have quantum computers built, that they'll be useful for anything and everything, and really do not understand that there's a lot of research still to be done on the quantum algorithms end of things. I think that's known very well to this community, but what I really want to emphasize is that this ability to play with quantum hardware, even with its limitations, allows us to do something that we really haven't been able to do much before, with the D-Wave being one exception to that. So there are provable advantages for, depending on how you count, a few dozen algorithms. We also know limitations, but for the most part, we don't know how quantum algorithms will affect certain applications. And at this stage of the technology, that is just not surprising, because if you look at classical computation, even for classical computation, it's hard to prove bounds on realistic cases. The analysis is just too difficult. And for a lot of the most complex computational problems, the best algorithms are just not known, and there's ongoing development of classical heuristics. And these are analyzed empirically. You run them and see how they do on problems of interest. And that's why there are, for example, annual SAT competitions, planning and scheduling competitions, machine learning competitions, et cetera, so that people can look at different approaches and see how they're faring. And it's only with quantum hardware that we can begin to play more of a role here. And really the next decade is going to be quantum heuristics coming to the fore. And the reason this is so important is that, just judging from the classical case as to where the algorithms for the hardest computational problems are, many of those are heuristic. And we will finally be able to really explore a wide variety of quantum heuristics coming forward. So I'm very excited about that and want to communicate that excitement to everyone here. And we'll now go on to talk about a specific case for these. And I'm going to talk both about quantum annealing and QAOA. And part of the motivation for that is that there's been a series of results showing connections between quantum annealing and QAOA, particularly between quantum annealing schedules and QAOA parameter setting. So, for example, Zhao and co-authors looked at a number of families of problems and found that for easy problems, QAOA schedules resembled adiabatic schedules. For harder problems, they resembled diabatic schedules. So very exciting in terms of tying these two together so that we can learn from quantum annealing something about QAOA parameter setting and vice versa. Mbeng, Fazio, and Santoro also looked at these connections and found connections again between adiabatic schedules and QAOA. There had been an earlier result of Yang et al. On Pontryagin's minimum principle that implies that optimal evolution schedules may be bang bang, but if you look at it more carefully, for a fixed amount of time. The procedure has a bang schedule for part of the schedule at the beginning and the end, but more like a smooth annealing structure in between. So this is all very exciting, and I'm excited that I believe Glenn, I didn't actually hear the talk because it was in the middle of the night for me, but I believe Glenn talked about this briefly in his talk in the previous session, and Lucas will be talking briefly about that in his talk coming up in this section. Really exciting work. There are ties between all of these approaches to quantum optimization algorithms. We have a phase separation operator that's based on the cost function, often just a direct translation of the cost function to a Hamiltonian, but also can include penalty terms to enforce constraints and some sort of mixing operator, most often the transverse field, which is just the sum of the X operators, but we'll shortly see the importance of other mixers. So just to set the stage, I think everybody here knows about these different approaches. So in the interest of time, I'll just continue on. I'll give you a brief summary of QAOA. It iterates between phase separation and mixing for P steps. And there are results showing that if P goes to infinity, it converges to an optimum, which is good. There were some exciting work for P equals 1, showing that it's hard to sample the output up to standard complexity theory conjectures, but that's a sampling, not an optimization result. Briefly beat the top classical approximation ratio for the problem of max E3 ln 2, but then inspired a better classical algorithm, which is a win. But currently the quantum algorithm for just P equals 1 lags for by a log factor. And you may say, well, what about P equals 2? Well, so far the analysis has just proved too hard. And later results, we have a new algorithm for Grover's search problem that achieves the same query complexity, but is in the QAOA setting. And if you just naively trotterize the Roland-Surf schedule for adiabatic optimization, for adiabatic quantum computation, you lose the square root speed up. So this is a non-trivial result, and also suggests that at least in some cases, you can find good parameters even for large P. So that's a setting. Now, we felt that it was important to generalize the quantum alternating operator ansatz to a case where not only do you have mixers, which are beyond just the X mixer and allow mixing in the feasible subspace only, but also are closely tied with the ability to implement them on gate model devices. And so instead of just having e to the I beta k HM for some mixer, we're splitting this up into a bunch of HJs. We still have just one coefficient beta k for all of those HJs. You can think of the HJs as the gates that can be natively implemented on the hardware, so can take into account what specific gates are implemented and constraints on which qubits they can be implemented between. And that gives you a somewhat more general mixing operator. And you can write down, as we did, some desirable conditions for such mixers such that they provide non-zero transitions between all feasible states. There's more work to be done here, but that's this generalization is promising. You will always want to start the system in initial state, which is a superposition of one or more feasible subspaces and can be prepared efficiently. So you want to start in the feasible subspace. So just to give you more of a sense for this, there are many problems that have Hamming weight constraints on a subset of variables. I'll give you a simple example here, which is a max K colorable subgraph. Here, we want to properly color the edges, meaning that each edge, the vertices at the end of that edge should have different colors. we're going to use a one-cut encoding where there are nk variables, where variable for a given vertex and color tells us whether that vertex is colored with that color or not. And we can then write the cost function as taking all the edges m and subtracting off the invalid, colors, the edges that have been colored with the same color at the end. And then we want to avoid invalid colorings where a vertex is labeled with two colors or not colored at all. We particularly want to avoid the second case where it's not colored at all, because a very easy way of optimizing this is to not color anything. So it's pretty important to make sure that every vertex is colored once and only once, and that gives us a Hamming weight 1 constraint. And under a normal transverse field mixer, you quickly lose that, even if you start in a state that obeys that constraint, you can quickly lose it. So instead, we want to use a swap or XY mixer that just swaps colors between at a vertex, so that your vertices stay with just a single color. And so there are a few different possibilities there. You can order all of the colors and do a ring mixer where there's only swaps between adjacent colors, or you could do a complete mixer that swaps between every pair of colors, or something in between the two. There are a variety of possibilities. That's one of the interesting things here, and there are trade-offs between the implementability of these mixers and how much mixing they do. Similarly, for the initial state, we could do something very simple, like choose a feasible state, like all vertices colored red. That's very, very far from optimal, about as far as you can be, but at least it's feasible. Each vertex is colored with one color. Or you could do something like a superposition of all feasible states, so a W state for each vertex. That's a little bit more that takes more gates to implement, and so there's a trade-off in the performance. So lots of possibilities here, lots of work to be done. I'll just mention briefly that when you're compiling these down to specific gates, you may need to, because these more complex mixers, the terms do not commute, you need to pay attention to ordering constraints. If you did a whole global operator with all these XX plus YY terms all summed together and wanted to get that exactly, that would be very, very expensive to implement. But we can break these things down into, say, all of the odd ones and all of the even ones, which all of the odd ones commute with each other. So XX plus YY, where the first vertex is labeled with an odd number. So in that case, we can implement those in terms of gates fairly easily, and then just alternate between the two once or more times. These have the desired properties of a mixer in terms of like reaching all the feasible states, not going out of the feasible subspace, etc. And there's a lot of work to be done to understand where which of these are best, and it will depend somewhat on the hardware. We have numerical results showing the advantage of the XY mixer. This confirmed the advantage because basically you're maintaining the evolution within a feasible subspace. And it's worth noting that as the number of qubits increases, the difference between these two exponential subspace, the ratio between the two shrinks exponentially with n. So with larger numbers of qubits, one gets better and better results for the XY over just the X mixer. As I've mentioned, there are trade-offs between mixers and initial states. And we have a result that's coming out shortly on showing that the XY mixer retains advantage under noise, but that for all of these things, noise remains a problem. And one nice thing is that when you have symmetries like this, there may be some things one can do with error mitigation that, that can help you a bit. So look for that. We hope to have that out next week. And We have also looked at depolarizing noise in max-cut QAOA. I think that understanding the effects of noise on both the performance of the algorithm and how it affects the parameters is very important for research going forward. And again, it's not just for QAOA, it's also for quantum annealing because of the close tie between annealing schedules and QAOA parameter setting. So take a look at that. Further on parameter setting, there's discouraging results from the Barron Plateau paper. There's more promising results from the QAOA Grover's unstructured search, as I mentioned. For the trivial problem of max cut on the ring, it was surprisingly hard to do the analysis. The fermionic view helps, as we showed, and then Bang and others have been able to push that further. And there are other results. It's a very active area. Recent results of Bravi for getting the expectation value, for example. So I want to move on now to quantum annealing schedules. One thing that a number of us pushed D-Wave to do was to add a pause to the anneal. And the intuition here was not that you wanted to slow down right at the gap, which is what you might guess from adiabatic quantum computing, but rather that you want to slow down after the gap in order to allow thermalization. And what I really want to illustrate here is that there's differences between quantum annealing and adiabatic quantum computing, and also between open system effects. And you really want to look at what happens in the non-adiabatic regimes and also what happens in open system regimes. And Zoe will be talking a bit more about this in her talk later. The theory has been pushed forward. There are recent papers, both of Tamim and Jeff, and also of Chen and Lidar, looking at understanding the theory of pausing better. And we have recent results that Zoe will talk about that show improvement in time to solution for a set of problems. But I'll leave that for her to go over with you. I also want to give a just hint at a different but very promising method here. And you can look at the energy matching problem. So given a classical state with a certain energy, it is generally hard to find another state with similar energy. And if this energy is up in a band where you have sufficiently many of these things, even if the probability of transfer is not high between far solutions separately, you can find enough paths there that you can get polynomial speed up in at least this random energy model. And a open question there was, when can you see that practically? So this is an asymptotic result, and when can you actually see this in practice? And Gianni will talk about this in his talk coming up. And what I want to emphasize here is the use of higher energy states in order to find, to solve hard problems. And not only does this affect the energy matching problem, but one could use this to do exploration in a higher energy band, and then use some sort of approach to, as you've moved further away, then do gradient descent or some other thing that can take you down lower to get an exact or approximate optimization algorithm into the lower energy states. So I think that this is a very exciting area that deserves to be explored more. And I also want to emphasize that for all of these things, it's really important to compare with classical optimization and sampling methods. And one of the things we've been very actively doing and working with a broader community is looking at what are some of the best classical optimization algorithms as there have been advances on quantum algorithms, are there things we can do with the classical algorithms that can keep up with the advances in quantum algorithms? So for example, the isoenergetic cluster moves was one of them. And this is absolutely critical for us to continue to assess the quantum advantage here and to not fool ourselves. So just wanted to advertise that and to talk about that one of the exciting things coming out of the field is physics-inspired classical algorithms, as well as just a stronger impetus to look at classical algorithms for certain types of problems with very novel techniques. And to emphasize that we really need to be careful in our evaluation criteria. So we should be comparing apples to apples. So if you have an algorithm that gives provable speed up, compare it to one that gives provable speed up or strong quantum speed up. Compare it with algorithms that give strong quantum speed up. And within numerical evaluation, you want to compare with the best approach, but look at whether they are tailored to the particular problems or not, because that can make a huge difference there. There's a lot of use for algorithms that are not so tailored and can be used generically. For example, often the problems we're looking at are subproblems that capture some aspects, but not all aspects of application level problems. And you would want to combine a bunch of those together. And so a non-tailored approach works for that. But tailored approaches are also, of course, very important for problems that when you want to solve the actual problem, as opposed to that just being a subset of what you'll ultimately want to solve. So with that, I want to give you some takeaway points. So the what I really want you to take away from this is that there are a bunch of promising approaches in quantum annealing going forward. Daniel mentioned a number of them in his talk. We've also looked a little bit at reverse annealing, but he covered that very well in his previous talk. We looked at pause. There's just more control over annealing schedules is very interesting. More general mixers. I should have said that Itai Hen and Surandri and Spedileri also have suggested general mixers in the adiabatic quantum annealing setting. And so there's synergy there. Also, the explicit use of higher energy states operating out of the non-adiabatic regime, where that may be explicitly helpful, open systems effects, ultimately perhaps going to engineered dissipation. We all talk about higher connectivity, more qubits, higher fidelity, et cetera, but I think these other aspects are really critical. Another thing I'd like you to take away from this is the synergies and even the blurring of boundaries between the gate model and quantum annealing approaches. So as I mentioned, there are strong connections between the two, but also in the hardware, gate model devices can be run in global modes. So for example, they can pulse between global Hamiltonians instead of breaking them down into 1 or 2 qubit gates. At least some of the hardware can be done in this way, which gives something between QAOA broken down into gates and between standard quantum annealing. And similarly, quantum annealing schedules can mimic gate model schedules. Another thing I really want to emphasize is that while people are concentrating on building the universal gate model hardware, special purpose quantum hardware can play a really significant role in the NISQ era. We've already seen that with quantum annealers and how much insight they've given. More quantum annealing work with these more sophisticated approaches will tell us more, but there's lots of opportunities, for example, for going after something with a population transfer methods explicitly that I mentioned briefly and Gianni will be talking about further. Looking at special purpose hardware for specific algorithms or specific types of algorithms, for example, certain types of simulation. So real push to see a real ecosystem of quantum hardware here. And the importance of advancing classical approaches and doing the right comparisons here. And also just how exciting it is that we are getting to play with quantum heuristics in a regime beyond where we could simulate before, and how that will likely lead to significant broadening of applications of quantum computing. So I like to end with a historical perspective. Back in 1972, the director of NASA Ames at the time brought the ILIAC 4 to NASA Ames. The ILIAC 4 was the first massively parallel computer. And at the time, as the fastest computer in the world, it had a 50 megaflop peak. And it had 64-bit CPUs. And I'm not missing any K's or M's or anything here. This is really where the state of the art was. And when I first came to NASA, there were people in the supercomputing division who were very puzzled about these early quantum devices, such as the D-Wave machine. But a number of the older folks who had been around in the 70s came by and said, we know what you're going through. We had to find good problems that would show off the challenge, the promise of these massively parallel computers. And it was challenging because these are very limited devices, and people were very happy with, for example, their wind tunnel approaches. And so there were questions at the time as to what really will be the applications of massively parallel computing. And I think we all know the answer to that. And so if we in the quantum computing community can be even a fraction as successful here as they were with massively parallel computing, we'll have made significant contributions to the world. So I will end there, and thank you very much.
Okay, thank you very much, Eleanor. We are a bit behind schedule, but so in the question and answer, there is a question, will participant get this presentation? Yes, these are recorded. By the way, they will be shown again in the final session, okay? This very presentation, I think, will be shown again. But they are all recorded, and I'm sure in the ICTP channel you can find all presentation. So if there is a very, very quick question, we can ask Eleanor. I see. Oh. No, I don't see any questions. Any questions from the panelists? Okay. Maybe we should move on. Now there'll be 4 focus talks.
Thank you to all the organizers. It's nice to be here, wherever here is for everybody. I'm going to talk a little bit about a couple of things that you can do with a new Advantage system. And I'm going to talk about what we've done with the previous generations of D-Wave processor and why we expect great things for the Advantage system. So already on slide 1, my information is out of date. Pegasus is now the current generation qubit connectivity, and Chimera is the previous generation qubit connectivity. So Advantage was put on the cloud last week, so feel free to go and check it out. In the current working graph, we've got 5,000, more than 5,000 qubits, something like 5,500, as opposed to 2,000 for the previous generation. We've got over 1 million Josephson junctions in this chip, and the maximum degree of the qubit connectivity graph has gone up from 6 to 15. So this allows you to embed things with less embedding overhead, as Zoe mentioned. And in particular, for the example of a 3D grid miner, where you could go up to 8 by 8 by 8 in the 2000Q system, you can go up to 15 by 15 by 12 in the current Advantage system. And furthermore, we have here, you can see you have these odd couplers. So the graph is no longer bipartite, which means that you can natively embed interesting non-bipartite systems. And so here, I'll excuse myself for the obscure link, but this is going to be recorded, so I don't feel too bad about it. This is a YouTube video on embedding things in the new architecture, and this is an archive preprint describing the new architecture and how to embed certain systems into it. And you'll note if you just look at the green qubits, for example, and delete the odd couplers, then you have a sub-chimera in the system. Okay, so what can you do with this graph? I'm going to focus on some finite dimensional systems that we have simulated in the previous system. And for all these except for one, the new system allows embedding with chains of length 2 instead of chains of length 4. So this started with Richard Harris et al.'s work on the 3D lattice. And we've studied a lot of two-dimensional systems in the meantime, including the Shastri-Sutherland lattice with Oak Ridge National Lab, quantum artificial square ice with Los Alamos National Lab, order by disorder and topological phase transitions in a quasi-triangular frustrated lattice. And one that nobody has looked at as far as I know is Buckminster-Fullerene, which you can actually embed with chains of length 3 in the D-Wave 2000Q processor, but in the Advantage processor, you can embed it without using chains at all. So I'll use this Buckminster-Fullerene as a nice example of important things that I want to communicate with people who want to do simulation of systems in the D-Wave processor. So the nice thing about having a non-bipartite graph is that you can put +1 on all these couplers, and because you have odd cycles, you have frustration. And so this is a Buckminster-Fullerene or a soccer ball graph, and all the cycles here have length 6 or 5. And one of the nice things about this graph is that it has tons and tons and tons of automorphisms, and we're going to exploit those automorphisms. So you'll note that each spin, I'll just separate these spins, the couplers by class. The blue ones are between 2 6 cycles, and the red ones are between a 5 cycle and a 6 cycle. So you have huge degeneracy if you just look at the antiferromagnetic case where everything is +1. You get 16,000 classical ground states. And in this Pegasus graph, you can actually embed 42 vertex disjoint copies using over 2,500 qubits. And you'll note that even though this seems like a sparse smattering of buckyballs, this is using more qubits than you had available in any of the previous processors. Okay, so back to the automorphisms, you'll notice that each spin is incident to 2 red couplers and 1 blue coupler here. And this graph is actually vertex transitive, meaning that there's an automorphism mapping this to this, any spin to any other spin. So if you take a soccer ball and you hold it such that some 5 cycle is oriented in some orientation facing you, you can do the same thing for any 5 cycle in any orientation, basically. And so this allows us to kind of study statistics of things that should be degenerate and sometimes are not. So I'm just going to use this as a canonical example, and I'm going to talk about some stuff that frequently or always gets relegated to the back matter of papers. And this is something that nobody really talks about very much in the front matter. And I think that it deserves a little bit more attention. So I'm going to give this a bit of a treatment. So there's been a lot of work on quantum simulation, and this has been the source of a lot of success with the D-Wave processors recently. And a lot of these simulations, especially when you're adding a transverse field to a well-understood classical system, this often relies on a classical system having very well-controlled degeneracy. And so you'll be familiar with the fact that whenever you have a calibrated system and you put an input on that calibrated system, you can sometimes change the calibration of it. So we kind of ship these processors with a one-size-fits-all calibration, and then if you're doing a simulation, you find yourself in a situation where you are spending a lot of time studying one system. And so when you're doing this, you can afford to make sure that everything is really well balanced. So for this example, I'm going to start by making sure that every qubit is balanced at degeneracy. So there's no H in this system, no longitudinal field. So we know that the observed magnetization of each qubit should be 0. So I'm just going to show an iterative method to balance the qubits. This is very simple stuff, and all we're doing is balancing out the crosstalk with a compensation. And if you Google this term flux bias offset, you'll find the documentation for the D-Wave processor if you're a user. So you initialize these offsets to be 0 by default, and then you iterate many times in a gradient descent method. So you anneal many times, and you can just average these samples that you get by spin, and you can look at the observed qubit magnetizations. You want these all to be 0, but they're not. And so what you do is you just update the flux bias offset on each spin by a step size multiplied by the observed magnetization. And I'm intentionally omitting the particulars of this because it's a general method, and you need to either fit your parameters properly or write a method that will fit it for you automatically, adaptively. Okay, so I'm just going to simulate the system again and again with whatever protocol I want. This happens to be a pause and quench protocol at s equals 0.4. And I'm going to show 300 iterations. So the first 100 iterations, I'm going to do nothing. And you can see that there are some systematics in the magnetizations that I'm observing. And then I'm going to turn on this gradient descent flux bias offset shim to balance the qubits to 0. And very quickly, we see these flux bias offsets jump away from 0. This is in microphi naught. And almost immediately, you see the systematic magnetizations that you saw in the first 100 iterations essentially disappear, and they're reduced to statistical noise or flux noise. So if you look at just 20 iterations here and 20 iterations here, so with and without the flux bias offset shim, you can see the histogram. This is all the qubits that we're working with, 2,500 qubits. And we expect these all to be 0, and they're really kind of spread out all over the place without the flux bias offset shim. And once we balance them with the flux bias offset shim, we get a really tight distribution. And this variance is essentially just statistical. If we continue doing this, we're going to get a tighter and tighter distribution, which basically becomes a delta function. So that's great. This makes our simulated degenerate system much more degenerate, and therefore we can observe quantum effects much more easily. And so I'm going to show the second approach, which is doing the same thing, except instead of balancing the magnetizations of the spins, I'm balancing the spin-spin correlations of 2 spins that are in a 5 cycle together. So I'm just going to do a coupler shim, and all of these start at +1. And for many iterations, again, I'm going to anneal many times, get observed spin-spin correlations for any 2 spins neighboring in a 5 cycle. And then I'm going to update the coupling between these 2 spins by a step size times the deviation from the expected value. Now, I happen to know the expected value, or the desired value in this case, because I very well understand the ground state manifold. But it's not necessary, because we're actually doing this for so many pairs of spins that you can just take the average of over all these pairs. So you're just homogenizing these correlations, you're pushing them towards the average. And let's see what this looks like. So I'm going to turn on the previous flux bias offset shim that I already showed after 100 iterations. And then after 200 iterations, I'm going to show the coupler shim. So already just balancing the qubits individually at degeneracy reduces a lot of the correlation systematics that you see, but some remains. And then as before, this is almost immediately quashed by the calibration refinement. So these are the histograms for no shim, flux bias offset shim, and the full shim with both flux bias offsets and couplers. And now we're getting much, much better statistics. Okay, so this is a kind of a cute example of a fullerene, which is a system that we can't study in the previous processor. But I'm going to show an example of why this is really important for quantum simulation by way of discussing our recent result on a scaling advantage over path integral Monte Carlo. And Daniel mentioned this. It's a result on a geometrically frustrated lattice with cylindrical boundary conditions. And I'll describe to you what the experiment is in a moment. But what we end up with is we have two open boundaries here, and they're not actually the same as one another. You get these pendant spins on this side, but not on this side. And if we're really being faithful to the symmetries in this cylindrical boundary condition, the only sets of couplers that we can actually group together and say these should have the exact same statistics are rotational symmetry groups. So we partition the couplers into these rotational symmetry groups, and we do the same thing as before. We tune the couplers so that the spin-spin correlations within this group become tightly grouped around the mean. So just to recap this experiment a little bit, we first published the feasibility in 2018, and then more recently we published a rigorous benchmarking study of it against path integral Monte Carlo. So what happens is you get a quantum order by disorder phenomenon where you have a highly degenerate ground state in what is essentially a triangular antiferromagnet. And from this emerges an approximate XY model. And as you get these topological features like vortices and anti-vortices in this model. And as you lower the temperature, assuming that the transverse field is small enough that you're not beyond the quantum phase transition, you get long range order eventually. So in this experiment, we're not actually able to get long range order because this is much colder than the temperature of the system, but we can get to an extended critical phase where we see the onset of quasi long range order. And we can quantify the order in this system via an order parameter that comes from this pseudo spin over here. And you can see that as we sweep the annealing parameter S, this is very quantum and this is very perturbative, very classical. For the very quantum case where the transverse field is large, our estimates are totally out to lunch. And this is because the readout quench of the system is not fast enough for the dynamics in the system. So the system actually macroscopically orders during the readout quench. But as long as this slows down sufficiently, we can get good estimates. Now, this order parameter is just the magnitude of a complex order parameter. And we're going to measure this using a measure in the middle quantum evolution Monte Carlo method, where we do basically a Markov chain Monte Carlo. It's a non-Markovian Markov chain Monte Carlo, where each step is a reverse anneal. So we have a classical state, turn on quantum and thermal fluctuations, turn them off, classical state again and again. So we get a chain of observed classical states. And this is kind of in the interesting region where gamma is close to J. And if we take the average over many, many repetitions of this protocol, we can see the expected statistics after 1 microsecond of thermalization, 2 microseconds, 3 microseconds, and we can see the convergence from a number of different initial conditions that are based on topological obstructions. Qualitatively, the convergence from these topological obstructions is very similar to path integral Monte Carlo. You'll note that this is about 3 million times faster than a CPU here. But we're more interested in the scaling result. But let me talk about the symmetries that we want to see in this system. So it happens to be that this complex order parameter should be continuously rotationally symmetric in the large system limit, which we're close to being in, modulo our boundary conditions. And so this is what we want to see, and this is what we do see. In fact, this is the output from the D-Wave processor at high and low temperature here. And this is just a classic complex order parameter. And this is path integral Monte Carlo. So we're seeing the desired rotational symmetry, and we're seeing essentially not just the correct average magnitude, but we're seeing the correct histogram of magnitudes and phases. But what happens if we don't do the calibration refinement? So if we don't shim the qubits to degeneracy, and we don't shim the couplers to degeneracy, then what we get is heavily biased towards some particular phase. So this is a problem for two reasons. First of all, we're not getting the desired symmetries in the system. And secondly, this anisotropy that you get causes a drag on the relaxation. So you want to think about this like a kind of a glassy pond that you're applying quantum fluctuations to, and you need it to be really flat for the dynamics to be fast and accurate, for the equilibrium estimates to be accurate and the dynamics to be fast. But you see, you can shim away the individual qubit magnetizations very effectively, just like I did with the Buckminster-Fullerene. But this still leaves some systematics in the coupling. And then you can shim away the coupling systematics using these rotational symmetry groups. And you can see that the correlations, the AFM spin-spin correlations, become a little bit different as you get towards the boundaries, but this is actually correct. You expect them to be different as you get towards the boundaries. So this is something that we're not overfitting, so that's good. So I mentioned a speed up result, and the two parameters that we want to tweak in this case are temperature and system size. And so as you lower the temperature, the convergence gets slower and slower, the dynamics get slower and slower for both path integral Monte Carlo and quantum annealing. But for quantum annealing, the slope is much more gentle than it is for path integral Monte Carlo. And this is in line with certain theoretical examples where you can actually outpace the tunneling of path integral Monte Carlo using a quantum annealer in some idealized limit. But this is an experimental evidence of this. And I'll also note that the advantage that we see, this is just this divided by this. So it increases as we get colder, but it also increases as we turn up the transverse field. So the more quantum fluctuations we get, the higher the benefit from the D-Wave processor. And although we don't have firm evidence, one might easily imagine that this is because of extended tunneling range. So in terms of system size, computer scientists would be more interested in this, and you get more gentle scaling in the D-Wave processor than you do in path integral Monte Carlo. So you see a scaling advantage in both system size and temperature. So probably for this particular audience, people aren't going to be very impressed by 1,000,000 times speed up over specialized code in a CPU, because we've seen this kind of thing before. But what is really special about this, in my opinion, is that this is a real world application to the extent that computational condensed matter physics is the real world. And that means that people have actually studied extremely similar systems, and they've done so using path integral Monte Carlo. So we're really not just cooking up some fake benchmark here. And so this is experimental evidence that we've really wanted for a long time, that QA can beat QMC in scaling. Now, this is not, as Daniel mentioned, this is not for optimization, but I think that this is a really nice example because you can really see what's going on in the middle of the anneal under the hood. So we would expect even better results from Advantage. And we haven't had much time to play with Advantage yet, but as I said, this is one of the examples where instead of having 4-qubit chains, you can go down to 2-qubit chains. So I'll just use that statement to segue to a small performance example in Advantage, which is on 3-dimensional spin glasses, which Johnny mentioned as well. But we're not simulating these in the quantum system. We're just optimizing spin glasses. So this is a pretty basic experiment, proof of principle, basically, with this new processor. So both of these 3D lattices have the same qualitative embedding in both Chimera and Pegasus. So I'm just showing the 6 neighbors of a single lattice site here. So you have 2 in each of the X, Y, and Z dimensions. So this is Y, up, down, X, left, right, and Z in, out, I guess. And these are 4-qubit chains, as seen in the Harris et al. Science paper. So in the advantage system, as I said, we can go up to 15 by 15 by 12, and we do so with 2-qubit chains with a qualitatively similar embedding. So just to go through this really quickly, looking at 100 random instances of each lattice dimension from 5 to 10, you can only go up to L equal 8 in the D-Wave 2000Q, and you can go up to 15 for the advantage processor, but I only went up to 10 for this particular example. What we're seeing here is the median and then 25th, 75th, 10th, and 90th percentiles of the 100 instances in these error bars. And you can see a pretty clear scaling advantage opening up over the previous processor. This is kind of almost an order of magnitude. And then in the 90th percentile, it's about 50 times improvement in time to solution. So what I've done is I've attempted to optimize the anneal time, but we can't find an optimal anneal time for the smaller instances. Looking at 100 random instances for 8 by 8 by 8, we can compare apples to apples. We've run the same instances on the two processors, and we see something that's very encouraging, which is that the advantage that we get from the new processor is the biggest for the hardest problems. So this is really encouraging for the kind of scaling advantage that we would want to see. We also see better consistency across cube isometries. So a cube has 48 symmetries or automorphisms called isometries. And this is an example where we're taking a spin glass instance. These are just plus minus 1 on the couplings, random bond model. And we're flipping this along the x-axis. So you can see that this is a mirror image of this one. And this allows us to actually run 48 different embeddings of each instance on each processor. This is 6 by 6 by 6, this data, and we can run fully yielded lattices on both chips. And you can see that not only do we see a scaling advantage for the new processor, the advantage processor, we see improved consistency with respect to these 48 isometries. So you see a much smaller variance. These error bars are the minimum and maximum for the 48 embeddings, essentially. And so this histogram shows the ratio of the best to the worst embedding, and you can see this ratio becoming smaller for the new chip, which is the kind of a consistency that we would expect from reduced embedding overhead. So I'll just touch on this very quickly because I've only got a couple of minutes left. This is a very recent collaboration with some people at the theoretical division at Los Alamos National Lab, where we introduced quantum artificial spin ice. For those of you who are familiar, artificial spin ice is a field of research where people essentially they literally fabricate frustrated magnetic systems using a variety of technologies, including lithographed nanomagnets. And so fine-tuning these is quite a lot of work. And we can do this reasonably easily in the D-Wave processor, given the appropriate embedding. And we can actually pin the boundary conditions in such a way that we can confine and study emergent monopoles. So one of the reasons why I want to show this, I'll skip over the details. We can see these monopoles walking around, but I just want to call out this system that we've embedded in the chip. There are a few defective lattice sites, and so these are represented by vacancies in the square ice system. So this system doesn't have any of the nice symmetries that I was talking about for the fullerene or for the geometrically frustrated lattice that we got the scaling advantage on. However, there's still kind of a get out of jail free card if you want to apply these calibration refinement methods that I've been discussing. And so the get out of jail free card is that you embed the system multiple times using local reconfigurations. And so even though this defective square lattice, it's a checkerboard lattice, it doesn't have any internal non-trivial automorphisms, you can actually map this 4-qubit chain to this 4-qubit chain in 2 different embeddings. And so that you can group and homogenize statistics by using that method. And that's a really nice way to get around this problem if you don't have symmetries in the actual problem that you're studying. Okay, so just to wrap up, I've used the fullerene example, which is a nice non-bipartite system that you can study in the Advantage processor to demonstrate some very basic and important calibration refinement methods that are really essential to getting good results out of simulation of highly degenerate systems. It's really important for suppressing crosstalk, and it's something that everybody does and nobody talks about it. So it's time to be open with each other and talk about how to get the best results here. And then just this 3D spin glass example is just a quick experiment that we've been able to do before releasing the Advantage processor, showing that these shorter chains yield better performance. And so there's lots of work to do. Please get on the system and help out. Thanks a lot.
Okay, thank you, Andrew. We're a bit behind schedule, but we started also a little bit late. So if there is any quick question, please ask from the panelists, just unmuting yourself or all the others in the Q&A chat. Okay. Let's see. Okay. No questions.
Actually, if I may, I have a question for Andrew. It's Daniel here.
Yeah, Daniel, please.
Yeah. So Andrew, with regards to shimming, is obviously this is something, as you say, you need to do all the time and you want to do all the time. Is it built into Advantage? Is it automated in some way?
No, it's currently not automated because the particular methods that you use for any given experiment, they tend to vary quite a lot. There would be ways of formalizing and automating it, but I think that probably doing so and getting the user to use these automated features, getting the right input for the appropriate automorphism classes, etc., would be just as challenging as cooking it up oneself. So it's something that we're going to work on, but I'm not sure how far we'll take it in terms of automation.
Okay. Other questions? If not, I think we can start with the
Sorry, one sec. All right, okay, good. Uh-oh, sorry, I technical, yeah, I think I might have hit the wrong thing here. I did hit the wrong thing, I think, sorry. Sorry, I shared the wrong thing there. Let me try again. Okay, good. Yeah, so please, I would like to get questions. I'm not sure if I'm going to be able to see the chat window during this, so maybe someone could interrupt with voice if there's questions, because I've given, longer versions of this talk online, which have been recorded. So if it's just a matter of giving the talk, you can certainly just watch those. So please give questions. So this talk is going to be about the computational power of the adiabatic algorithm with no sign problem, of adiabatic quantum computing with no sign problem. So what we imagine, right? We imagine, hopefully everyone can see, there we go. We imagine some path of Hamiltonians like H sub s, there'll be some parameter s, which is going to be a linear combination of two different terms. There'll be a driving term, 1 minus s times x, where x will be, say, some Pauli transverse field. It's the sum of x sub I on a bunch of qubits, plus s times some objective function, h sub z. And at s equals 0, everyone knows, assume in this audience, that the ground state is easy to repair. At s equals 1, this might encode the solution of some optimization problem. And if the gap does not go too small, as you go from s equals 0 to s equals 1, then you'll succeed in going from the initial easy to repair state to the ground state of your optimization problem. So we can ask, what is the computational power of this model of adiabatic quantum computing? So if you restricting, let's say, to the case in which the gap between the ground and first excited state is only polynomially small, so you can do the path in a polynomial time, ignoring all realistic questions about excitation to higher states, decoherence, and so on. If you don't impose any restrictions on these two Hamiltonian terms, x and h sub z, and they're just arbitrary local Hamiltonians, such that the first one you can prepare efficiently, then the answer is completely clear. This is equivalent in power to standard quantum computing. This is an old result of Haranov and collaborators from a long time ago, I think more than 15 years ago. But you might wonder about the special case. What happens when we impose this condition that there is no sign problem? What we mean in general for no sign problem, to say a Hamiltonian is no sign problem, people use the word stochastic, but I just personally, it sounds a little weird to me, is that all the off-diagonal matrix elements of the Hamiltonian are non-positive. So if you have some h sub ij, and now I'm going to use the subscripts to denote matrix elements of the Hamiltonian some preferred basis, these are all less than or equal to 0. And in this case, you want it to be true for all s in this interval. S goes from 0 to 1. Now, once you impose this condition that there's no sign problem, the problem gets easier to treat. For one thing, if you just ask for the problem at a specific value of s, you just say, okay, a particular Hamiltonian with no sign problem, ignoring all this question of adiabatic evolution and so on, just give a particular Hamiltonian with no sign problem. You can ask about its computational power. And this has been, there's an algorithm that's very successful often in practice, quantum Monte Carlo, at simulating this. It can get stuck. It's a Markov chain algorithm, and it can get stuck like any Markov chain algorithm can. But work of Terhal, Bravi, and others, I don't remember all the others, have shown that this is computational class, it's either MA or AM, I forget exactly, but it's basically it's believed under some de-randomization assumptions to be the same as NP. It's a little bigger than NP, but it's believed under de-randomization assumption. It includes NP, it's believed to be the same under some de-randomization assumptions. Believed not to be quite as big as QMA. So now you might ask the question, well, what if we combine these two restrictions? If we combine this restriction that the Hamiltonian has no sign problem, and you also say, we're going to start with some easy to prepare Hamiltonian, some Hamiltonian where it's easier to prepare the ground state, and we're going to follow an adiabatic path. For simplicity of presentation, we'll not necessarily assume that this path is a linear combination of two things, but I think with some gadgets, you could reduce it to that case. Well, imagine that you follow an adiabatic path of Hamiltonians with no sign problem, starting with something easy to prepare the ground state, keeping the gap from becoming too small. It can only become polynomially small. The path should not be too long. It should be only polynomially long. You have all these different things like the matrix element should only be polynomially big and so on. The Hamiltonian should be polynomially sparse. And ending at some final Hamiltonian, you want to ask, what is the power of this model? Is this model, it's at most BQP. It's at most this MA. So it's somewhere in the intersection. You might wonder, is it just P? Is it just what you can do in a polynomial time classical computer? So the point of this talk is to prevent strong evidence that it's not, that it's more powerful than anything you can do on a classical computer. And the basis for this evidence is showing that what we call relative to an oracle, it can't be simulated efficiently classically. What does this relative to an oracle mean? This is a standard thing in computer science, but I had to learn this coming from a different background, and maybe it's worth saying a few words about it. If you just ask for the problem of, here's two different Hamiltonians, which are some local terms, like this x and h sub z, and maybe x is this Pauli term and h sub z is the sum of zi. Well, this thing is in BQP. And no one has ever proven that BQP is different from P. That would be, a completely earth-shattering result in computer science. Even much weaker things would be earth-shatteringly powerful. So we don't expect to prove that. But what you can often prove is that relative to an oracle, you imagine that there's a black box, and this black box will answer certain questions. In this case, the black box, what it will do is you'll tell it a particular value of this parameter s, and you'll give it a computational basis state. You'll say, starting from this computational basis state, what are the other computational basis states to which we have non-vanishing matrix elements, and what are those matrix elements? And the oracle will answer. And you can keep querying the heroic oracle. You can start with a particular one, query ones that you can reach from that, query ones that you can reach from that, and so on. And this kind of setting is one in which hardness results are proven. And it's a natural one to consider, because if you look at all the kinds of optimization, kinds of algorithms for simulating this problem, they basically call some function that returns the value of the Hamiltonian at particular choices of parameters. So I'm going to prove that relative to an oracle, this can't be simulated classically. I'm only going to very quickly sketch it in the time allowed. So no variant of these programs could do it. Maybe there's something very complicated that uses some structure of the Hamiltonian, but we believe it can't be done. Now, let me say, for me, the motivation is not necessarily the adiabatic algorithm. I think if we ask about the applications to optimization, I think there's, in my opinion, overwhelming evidence that if we just take this H sub z to be some completely unstructured optimization thing, some completely unstructured term, like coming from some max 2 set, then 1 second. I'll be there in a little bit. Okay, I'm talking. Hey, bud, I'm giving my talk. Okay, I'll be back in a minute. If you have some, if the H sub z is some max 2 sat or whatever, and X is just this transverse field driving term, you should generically expect that the gap is going to be super exponentially small. This algorithm is not going to do well. So if you want to look for cases where the adiabatic algorithm does well, you need some kind of structure in the objective function. And the examples I'm going to construct are going to be some very complicated structure in the particular Hamiltonian. So before, though, that we try to break all classical algorithms, let's try to break the most natural, commonly used classical algorithms. There are other ones. And the most natural, commonly used classical algorithm is path integral Monte Carlo. So the idea of path integral Monte Carlo is that you have, it will often suffice not to compute some properties of the Hamiltonian, but to look at the partition function. So if we have just some fixed Hamiltonian rather than this parameter dependent one, we have some partition function, which is the trace of e to the minus beta h. Beta is the inverse temperature. As beta gets large, this e to the minus beta h will converge to some projector onto the ground states. And if the gap is only polynomial small, beta only needs to be polynomial large to get this to good approximation. You can use a path integral for this. So there's a number of different forms of the path integral, but what you can imagine is that we have some time parameter, imaginary time parameter tau that goes from 0 to beta. And we have some configuration of the system. Now, of course, the configuration of the system is really maybe the state of all these spins, if it's made out of n different spins or whatever. But I'll just draw it on a single line for schematic purposes. And what you consider is paths where it stays in some configuration, jumps to some other configuration, stays in that one for a while, jumps, and so on. You look at periodic paths because we're looking at a trace. You can also consider ones with open boundary conditions. And each of these paths comes with some weight. And the weight comes with 2 different factors. One is when you stay in a state for a while, you get a weight that's e to the minus beta h times the diagonal term for that state. And then when you jump from one state to another, there's a weight that's the matrix element between those 2 states, proportional to the matrix element between those 2 states. So the nice thing is that if the Hamiltonian has no sign problem, not only do you sum over paths, but you sum over paths with all the weights are non-negative. So it's just like a classical partition function. You're summing over a bunch of configurations rather than the configuration a single time. It's the trajectory, and they come with some weight. And so you can apply standard algorithms to do sums over to do sums over configurations like a Markov chain Monte Carlo. So you start with one configuration, which will be an entire trajectory. You allow a jump to another configuration, a jump to another configuration. You accept or reject according to some metropolis probabilities. If you're lucky, you might be able to figure out some cluster moves where you allow more complicated moves all at once. And then by doing this, if you don't get stuck, then you can sample the properties you want. But of course, in general, you will get stuck, right? A particular example of a Hamiltonian H would be just a completely diagonal Hamiltonian, a classical one. And then this becomes the same thing as classical Monte Carlo for a classical Hamiltonian. And we know that that gets stuck all the time. So by summing over these things, we know in general you'll get stuck. But the question is, in this particular case, will it be possible to take advantage of the adiabatic path to get rid of this getting stuck problem? So people have tried a very natural algorithm, which is that you start at s equals 0, you equilibrate, you change s a little bit, you equilibrate some more, you change s a little bit, you equilibrate some more. And what you might hope is that there would be some relationship between the equilibration time of the Monte Carlo and the gap of the Hamiltonian. And there's one particular case where there is a nice relationship between them. Imagine that we have a Hamiltonian, and now I'm going to draw again a one-dimensional graph, and this really would be for particle in one dimension. So you have some potential v of x, that depends upon some parameter x. That is the worst line I've ever drawn. Sorry, it's hard to draw on this vertical laptop screen. Imagine that the potential is some double well potential. So it has like a single well that's a deep and another one that's there. So initially the ground state is here. Now imagine that we take the well on the left and we imagine slowly changing the height of the well, making it a little deeper, and then a little deeper. Well, as we lower the well on the left, eventually the ground state, instead of being mostly localized in the well on the right, will go to mostly localized in the well on the left. And you can ask two questions. One, how big is the gap, right? I mean, if there's very small tunneling amplitude between the two wells, then right when the heights of the two wells are the same, the splitting between the two lowest energy states will be very small. It'll be proportional to that tunneling amplitude. At the same time, you can also ask, how quickly does it equilibrate? Initially, you're in some configuration where the right trajectories are all in one well, then they're all in the other well. And how quickly can you equilibrate as you sweep it? In this case, it turns out there's a very tight relation. You know, if one of them is polynomially small, then the other is only polynomially small. In this case, the simulation will succeed when the adiabatic algorithm succeeds. But there are other examples. And this is something that Mike Friedman and I looked at a lot, where you can make the gap not become small, but keep the gap of the Hamiltonian large, but you can make the equilibration time get bad. And as an example, imagine now I'm going to change the, so this is really like trying to construct things which will break path integral Monte Carlo by making the gap stay big, but making the equilibration time get long. And one of the problems is that this path integral Monte Carlo looks at trajectories. And so you can imagine a situation, I'm going to imagine a situation where you have the particle can kind of live on a figure 8, or it can live on another site, which I'll denote x, and there's a hopping between the two things. And what I want to imagine is that I start initially on the x, I'm going to tune the energy on this x, I'm going to tune the strength of this dashed line hopping. I'm going to start with the energy on the x very low, and the hopping weak, maybe the hopping 0. So initially, the particle is always on that x. That's just a single state, maybe. Then I start to turn on the tunneling between the x and some specific point on the figure 8, and I raise the energy to the x. Then I slowly turn off the tunneling. And either at the end, the particle will wind up on the figure 8, or it will end up on the x. And the thing that will determine it is whether the ground state energy on the figure 8 is above or below the ground state energy of the x. That there are some questions about, like, can we keep the amplitudes large enough between these and so on to keep the gaps not too small? But, you know, if we do it slowly, that's what will happen. Now, path integral Monte Carlo has a problem. If you look at the trajectories you should be sampling, they should jump onto this figure 8, make some loops around the figure 8, and go off. So in general, a trajectory might jump onto the figure 8, go around, and then jump back off, or go around the top loop and then the bottom loop and so on. And you can describe these trajectories by some words. I'll write an A if you go around the top loop, and a B if you go around the bottom. And in general, a trajectory might be some kind of complicated combination, like A, B, A inverse, B to the minus 2, and so on. Describe me. Go around the top loop, around the bottom, back around the first, 2 times or back around the second, and so on. There are words in a free group, the fundamental group of this particular thing I've drawn. But path integral Monte Carlo gets stuck in one trajectory. It can only stay in one particular trajectory. And there's a, in one particular topological sector, sorry. It can go around the top loop, but then it has to come back off the top loop, or else it's not a well-behaved trajectory that it's sampling. And in this particular case, if you look at a word on the free group of length proportional to the inverse temperature proportional to beta, the number of them is exponential in beta. So path integral Monte Carlo will misestimate the weight of the trajectories on the figure 8 by an amount that's exponential in beta. That means it will misestimate the energy on the figure 8 by an amount of order 1. So it makes a large error in the energy, and in the end, it winds up incorrectly deciding where the particle should go. Now, this, of course, is a specific algorithm. The goal is, from a theory point, well, from a computer science point of view, maybe it's interesting to ask, can we beat all algorithms? Can we come up with something where no algorithm will succeed? There have been other algorithms, for example, diffusion Monte Carlo, and there was work by Jordan and collaborators on that, and they showed that you can make that one fail by looking at obstructions having to do with L1 versus L2 norm. Open world line Monte Carlo, Mike Friedman and I studied that. That involves combining this topological obstructions with some use of L1 versus L2 norm, and so on. So the question is to come up with something that makes every algorithm fail. And this is what now we know you can do within this Oracle model. And the key is to use this topological obstruction. And first, there's a certain, I'm going to just only have time to very, very quickly sketch the construction. The idea is first to make a certain reduction. So this construction is going to have some graph. What I mean is we're going to think about a discrete space of states where there's going to be some graph of possible configurations, some hopping between them with certain amplitudes. And I'm going to also think about having this X somewhere. And I'm going to think about particular cases where I just change the energy of this X and change the tunneling on and off this graph. And what I'm going to look for is I'm going to look for two different graphs, which have the property that their ground state's energy differ by a good amount, by a decent amount as quantum Hamiltonian. So that in one case, depending upon how I tune the energy of this X, you should wind up on one side. In the other case, you should wind up on the graph. In one case, you should end up on the X. These graphs represent possible states, and the edges represent non-vanishing matrix elements between them. And I want to arrange it so that the amplitude of the ground state on this graph has a reasonable amplitude on this state that the dashed line connects to. That's otherwise the tunneling between will be small. And this is kind of a cartoon of the adiabatic algorithm. It's just carrying really the essential features of it, that like the inverse polynomial gap carries into this inverse polynomial amplitude to tunnel on and off. And it's just looking for graphs with certain properties that are hard to distinguish classically, but quantumly have rather different energies. Even though the ground states still have amplitude on a certain site, but they're very hard to distinguish classically, even though quantumly the energy is different. Now, there's some more steps in order to proving that this means you can't solve the optimization problem. Because in this particular case, you just say, oh, I'll just try the two possibilities. Either you're on the graph or not. I just run, I just force one of the two to happen and try them both. So there's some other steps to making it so that if you can't solve this problem, then you can't solve what the adiabatic algorithm can solve. So we look for two graphs which are hard to distinguish. Now, another step is when I talked about the path integral Monte Carlo, I was saying that it has trouble with topological sectors. So imagine some path that on this graph that starts, at this site here. Oops, I didn't mean to do that. I hit the wrong thing. Sorry. Starts here and then hops onto this site, hops onto that site, and hops back to where it starts. In this case, the algorithm can see, a classical algorithm can see, oh yeah, I returned to where I started. And so it can start to figure things out. I want to make it impossible for a classical algorithm to know that it's returned to where it started. I want to make it so that when it moves on a graph, it's blind. Essentially, all it can see is how many neighbors do I have? And it can query a neighbor and ask, how many neighbors does that have? But it never knows when it got back to where it started, unless it gets back to that one particular vertex, which couples to the X. And the way we do it is we take this graph and we sort of blow it up. We take each of these small dots and we replace it with a large number of little dots. Same thing here, exponentially many. And we replace each of these edges between them. So there's an edge between these two small red vertices with edges between all the dots in them, but in some totally random way with some random permutation applied when you go from one to the other. So you're hopping along, and as you hop from one edge to another, you just go from one of the dots here, one of the little vertices, to a completely permuted one over there, to a permuted one over there, and a permuted one over there. When you follow a loop on your original graph, the odds are when you go to these little vertices, you won't return to where you start, and so you won't recognize it. So you make it so that your classical algorithm is essentially blind to all information about the graph, except as it walks, what are the number of neighbors? And at this point, we reduce the problem to building two graphs where if all you can do is do this walk blindly and ask about the number of neighbors, where classically you can't tell the difference, but quantumly there is a large difference. And this is such a construction exists. The construction is based on starting with a particular graph, which is, what is this graph? You take a line, a short line of some length. So I'll just draw it as, say, 5 long here. And I have 5 long and 4 high. And what you do is everybody couples to everybody in the neighboring edge. So like that goes to that, to that, to that, that goes to that, to that, to that, to that, and so on here. So it's a particular graph which you can move around on. And then you start somewhere in the middle, and I either connect the left edge to the right edge or not. The two different ones, and connect means everyone on the right edge goes to everyone on the left edge. I connect them or not. And that change causes difference in the energy. Now it'd be easy to tell the difference you just having those connection or not. You just start somewhere in the middle, do a random walk, and eventually either you hit one of these vertices on the edge, in which case you have fewer neighbors because it only has neighbors back to the inside rather than to the other side, or you don't. So this is an easy one to solve. You just do a random walk and you hit the boundary or not. But then what I do is I take the graph and I decorate it. On every single vertex, I attach a tree, which goes for some depth, like that. And then the tree, sorry, my it's automatically correcting some of it to triangles. But you just attach a tree off every vertex. So now when you random walk, you tend to get lost on the tree. So you start, you walk, you walk, you walk, you get, by chance, you take a step onto the tree, but you can't tell the difference. You know, when you're on the graph, it's very different from the tree because there's all these self loops, but the classical algorithm can't tell that. You take a walk on the tree, eventually at the end of the tree, maybe you realize, oh, I shouldn't have taken a walk on there. I better go back to where I start. That slows the classical algorithm down a lot because it keeps taking all these false steps on the tree. But it can still do it in polynomial time. But then you decorate the tree with more trees and more trees and more trees and more trees. And you make this situation where the quantum algorithm, what the quantum wave function does, the quantum wave function stays concentrated on what I've drawn in black because there's all these self loops. And as a result, the L2 norm of the wave function is quite big there. But the L1 of the norm of the wave function is quite big on these other trees coming off. And the classical algorithm, since all it can do, I mean, anything can do when it queries the oracles, just get neighbors and pick them. And there's no way for it to avoid by chance following these trees. I mean, there's a lot of steps to proving that there's no way to do it. But no classical algorithm can do it. And one can then show that there's a lower bound of n to the log n on the time for any classical algorithm to solve this. Time, I should say number of queries to the oracle. This allows the classical algorithm to do any kind of computation it wants. It's bound based on the number of queries to this oracle. So let me just close in the 2 minutes that remain. Two interesting questions. One is, this is barely super polynomial. It's n to the log n. It's not 2 to the n. It's not polynomial, but it's barely super polynomial. So you can wonder, can it be improved to something that's like, 2 to the square root n, or maybe 2 to the n? Can you really prove a real slowdown for something that's, not this quasi polynomial time? Prove something that might be an exponential slowdown for the classical algorithm? Or conversely, can you prove that one of the known, or perhaps some new classical algorithm, always is able to do it faster than exponential? The naive worst case algorithm is still exponentially slow. Can we prove something faster classically? And then the other one is, just to a very, very optimistic and broad thinking way to say it. There was Shor's algorithm, of course, which had an enormous impact on the field of quantum computation, cannot be understated. But there's also Simon's algorithm. And Simon's algorithm is an algorithm there you provably have a, I think, exponential speed up of quantum over classical, but it's exponential relative to an oracle. Now, if you take that particular oracle in Simon's algorithm and instantiate it in a particular way, you get Shor's algorithm. There's not a proven speed up in Shor's algorithm, but we know no classical algorithm that matches it. So here we have a particular oracle, and relative to this oracle, which answers very strange questions about graphs, we can prove that this quantum algorithm has a speed up. Now, can we come up with an instantiation that will be some actually useful case where there's some useful quantum algorithm? I don't know. I would be a great question if anyone could have some useful thoughts on that. So let me stop here and take questions.
Okay, thank you very much.
Annealing and the sign problem. The role of the sign problem in quantum annealing has been, I would say, a major guiding question in our field in the past decade, stochastic versus non-stochastic Hamiltonians. And there's been some big developments this year, and I would say that this year is a turning point in our understanding. So two of the main questions to consider are, when do we know for certain that classical algorithms can efficiently simulate stochastic quantum annealing? And maybe the more interesting question, so will non-stochastic Hamiltonians enable that elusive scaling advantage, specifically for optimization with quantum annealing? So on the topic of stochastic simulation, the main result of the year is this new oracle separation that Matt Hastings just presented. I also want to briefly mention some work that I did with my student on high temperature simulation results. But most of my talk will focus on the second question about non-stochastic advantage. And so here in this paper, we define a new de-signing map that from non-stochastic Hamiltonians to stochastic Hamiltonians. And this allows us to compare them somewhat directly in the setting of adiabatic optimization. And the conclusion is that the d-signed stochastic Hamiltonians tend to have larger spectral gaps. And so we are calling into question the prospects for a non-stochastic advantage in optimization. Now, I'll qualify that carefully as we go on. But first, just talking about the status of stochastic simulation. So, Hastings' proof of this oracle separation, a superpolynomial oracle speedup, resolves a problem in Hamiltonian complexity that has been open for at least 15 years. So that is, I would say, one of the highlight results of the year across all parts of quantum information. Okay, so going in the other direction, so can we prove new simulations for stochastic QA? So this result that we had earlier this year says that path integral quantum Monte Carlo converges efficiently for generalized transverse Ising models, the kind we usually consider, at temperatures above 2 times the interaction degree plus 2 in units of the coupling. So you can actually insert, h bar in Boltzmann's constant and turn this into a practical sounding result. That is, if you have your interaction degree of 6 with couplings of 1 gigahertz, this temperature above which we guarantee efficiency of quantum Monte Carlo would be 800 millikelvin. Now, obviously, that's much warmer than current superconducting devices. So no one is proposing to get a quantum advantage at those temperatures. We're off by maybe a factor of 10 or more. But I think one of the main things I want to say about this result, so we now have 3 general conditions that imply rigorous quantum Monte Carlo simulations of transverse Ising Gibbs states. These are 1D transverse Ising systems at any constant temperature, ferromagnetic systems, even down to inverse polynomially small temperature, and then this recent result of high temperature systems. And so what's notable about these 3 cases are these are the same 3 cases for which we know efficient simulations of Gibbs states of classical Ising models, because these are the cases that avoid NP hardness. So the stochastic simulation story between these 3 results and also the oracle separation of Hastings may be complete in terms of natural questions that we have a reasonable hope to answer with the theoretical tools we have. But we've known in this community, we've had practical evidence for many years that quantum Monte Carlo is efficient. So this is just the rigorous results catching up to what we've seen in benchmarking. So the real question is, what can we do with non-stochastic Hamiltonians? Just reminding ourselves of the history, we started to turn attention to non-stochastic Hamiltonians as it became increasingly unlikely to find a scaling advantage with transverse field annealing. So the main arguments for turning to stochastic Hamiltonians have been, non-stochastic Hamiltonians have been indirect. So adiabatic computing with non-stochastic Hamiltonians can be universal for quantum computing. But it'll be relevant for this talk that the final Hamiltonian in these universality constructions is much more complicated than a classical optimization Hamiltonian. Okay, another argument for non-stochastic Hamiltonians is that we've known for 40 years, 50 years, that practically efficient quantum Monte Carlo simulations break down in the non-stochastic case because of the sign problem. Okay. But neither of these arguments directly implies that we'll see an advantage in non-stochastic QA for optimization. So the message today is, well, we'll introduce this designing mapping, and it allows every non-stochastic Hamiltonian to be compared with a stochastic counterpart. And we find the stochastic counterparts almost always have larger gaps. But it is a probabilistic statement. So it does not contradict important existing results like the exponential improvement by non-stochastic interactions in the p-spin model. Our results really just imply that inserting random non-stochastic terms is unlikely to provide an advantage. So here is the definition of the designing operation. It simply just forces all the off-diagonal matrix elements to have the same phase, the phase they would have if the Hamiltonian were stochastic. So here is your original Hamiltonian written out in terms of its computational basis matrix elements. And here's the designed Hamiltonian, H bar, where we've just left the diagonal elements unchanged, but we've forced all the off-diagonal elements to be real and non-positive. So right away, this designing is a nonlinear map. It changes all of the eigenvalues and eigenvectors in general. But the key point is that it leaves classical Hamiltonians unchanged, this diagonal part. And so it preserves the endpoints of an annealing path. The designed Hamiltonian can therefore be regarded as a new path through the space of Hamiltonians that connects the same endpoints, the same classical Hamiltonian endpoints as the original Hamiltonian path. And this property of preserving the endpoints is crucial. So designing would not make much sense to consider in universal AQC, where the final Hamiltonian wouldn't be preserved. Or say you were doing adiabatic quantum simulation and you were trying to prepare the ground state of a final Hamiltonian that is itself non-stochastic. Well, then it wouldn't make sense to consider this mapping. It's really specialized to this optimization setting. And then the other thing to mention is that this designing always preserves the sparsity of the Hamiltonian in the computational basis, right? You only have non-zero entries in H bar where there were non-zero entries in H. So it compares the non-stochastic interactions to what are effectively multi-spin stochastic interactions. So we're not just comparing non-stochastic to the plane transverse field, but we're comparing, if you like, plus XX to minus XX. Okay, so because this designing operation is highly nonlinear, we were not able to rigorously analyze it in all generality. So our message that designing increases the spectral gap is based on a variety of suggestive evidence. First I'll describe a relatively quick rigorous proof in the setting of random matrix ensembles, Wigner matrices. So our paper just contains a collection of results. We also show that in certain special cases, for example, let's say your Hamiltonian is written purely in terms of Pauli X operators, and you design the matrix elements in the computational basis. Well, this always increases the spectral gap. So we have some kind of complicated results that relate to the geometry of the ground state probability distribution. And one way to sort of efficiently summarize these results that I won't go into is that if the ground state probability distribution does not change much under designing, so of course the non-stochastic Hamiltonian has non-trivial phases in the ground state, but when you square it, you get a distribution. Right, and if the original Hamiltonian and the designed Hamiltonian have similar ground state probability distributions in the basis where you designed, then on geometric grounds, designing cannot shrink the gap by much. So we don't necessarily show it increases the gap in this setting, but that if these are close, and this assumption of closeness kind of helps deal with the nonlinearity. But maybe the most convincing thing for many of us is a very clear trend in numerical simulations that R emerges at low qubit number. And so all of our analytic arguments support the main conclusion, but what we would really like to address, I would say, are random local Hamiltonians or local Hamiltonians with random non-stochastic catalysts. But these are the most difficult to analyze. So there we rely a bit on a numerical trend, but we can't actually prove the result that the numerics indicate. So there is an open problem here. Okay, so as a first kind of warm-up result, an initial observation is that designing always decreases the ground energy. And the proof of this is just variational. So you start with your original Hamiltonian and your original ground state. Then your proposed, your variational ansatz for the new state, the designed Hamiltonian's ground state, is just the absolute value of what you had before. And here, this inequality is the variational theorem or variational method, and this you just show by algebra. So this feature, which always happens, the decrease in the ground energy upon designing, this is, in some ways, I think the main reason why the gap gets bigger is that the rest of the eigenvalues, they do all kinds of things, but you consistently have the ground state energy dropping, and that tends to create a bigger spectral gap. So as we know, stochastic Hamiltonians are special in their ground states particularly. And so just from this observation, so if the Hamiltonian is positive semi-definite, and we don't change the diagonal elements, well, then the trace of the original Hamiltonian and the designed one are equal. So if you think about it, we have a sum of the eigenvalues. They're all non-negative. They have to add up to some value. We've decreased the smallest one when we design. So this has to increase the spacing somewhere in the spectrum. And if we could just show that the first excited energy of the designed Hamiltonian for some reason got bigger, well, we would be done. But this just isn't true in general. In fact, what tends to happen is that the designed first excited state also goes down a bit, but not as much as the ground state. And that's the reason you get a bigger gap. Okay, so what can we prove? So let's consider an ensemble of n by n random symmetric matrices, let's say with IID entries of mean 0 and variance 1. So Wigner famously showed that the distribution of eigenvalues of these matrices is a semicircle distribution between plus and minus root n in this normalization I'm choosing. And this fact also holds for entries chosen uniformly, say, which we'll use. So it really just depends on the first few moments of the distribution of the IID entries. And since there are n of these eigenvalues, the typical spacing between them is 1 over square root n, because it's root n to root n. And then, a lot is known about the probability that these spacings differ by very much. And also, there's a whole theory of what's happening at the extreme eigenvalue. So we're about to think of stochastic Hamiltonians and ground states in terms of Hamiltonians with non-negative matrix entries and their top eigenvector. So kind of as playing the role of the stochastic Hamiltonians as a random matrix ensemble. So consider an ensemble of symmetric matrices with non-negative IID entries, say chosen uniformly from the interval 0 to 1. And this should be mathematically equivalent. These matrices with non-negative entries and their largest eigenvector are just directly related to a stochastic Hamiltonian and its ground state. Just a shift in rescaling. So basically the point is that each matrix in this new ensemble of non-negative matrices can be obtained from a matrix in the previous ensemble by adding a matrix that has a 1 in every entry. And so this matrix that we're adding has a single huge eigenvalue of n, and all of its other eigenvalues are 0. It's a rank 1 matrix. And so you can just show using some basic tools like Weil's inequality on the eigenvalues and some variational method that what happens is the largest eigenvalue just becomes an outlier. So you've increased the gap tremendously by designing. And so maybe it's not so meaningful or just in terms of the normalization, but basically, you get an arbitrarily large separation between the standard Wigner ensemble, which is related to the GOE ensemble, and this non-negative ensemble. Okay, so if that didn't convince you, here's what the numerics look like for random dense matrices with IID entries. So we define this notion, which is the fraction of non-stochastic winds, So n is the dimension of the matrix. So these are dense matrices. Basically what you see is that the fraction of non-stochastic winds, which are cases where the original Hamiltonian has a larger gap than its d-signed counterpart, that these go to 0 rapidly with the dimension of the matrix. So this is just saying that, all but this 10 to the minus 6 fraction of these guys have a larger spectral gap when you d-sign them. So it's just confirming what we could prove mathematically. And then the d-signed case actually just is worse. Sorry, the complex valued case is just worse than the real valued non-stochastic case numerically. Okay, here's some more numerics on these results. So yeah, so we considered max cut problems on 3 regular graphs. There's a lot of different studies you could do on this, but we settled on these, and we considered several different cases. So we considered these alpha ij coefficients on the non-stochastic path change could either be randomly plus or minus 1. They could be uniformly random in the interval -1 to 1, and then the Hamiltonian is fixed as max cut, taken from some graph. And then, if you're really kind of an expert in this, here's another sort of case breakdown we consider. So the Hamiltonian that we've written here has a global bit flip symmetry, and the time evolution in the pure unitary case is constrained to the +1 subspace of this symmetry. And so Tamim Albash had a paper where he explained the non-stochastic advantage in the Peaceman model, or related it to a condition on whether or not the ground state energy is in this +1 subspace or not. So the two things that could happen, right? You're sort of trapped in this +1 subspace, and the question is the true ground state energy at the point of the minimum gap, is it outside this +1 subspace? And this seemed to somehow be related to non-stochastic examples of non-stochastic enhancement that Tamim looked at. So here's a bunch of numerical data. So let's first focus on this upper square, where we're looking at exactly the de-signing proposal I told you about, and we're just looking at the minimum gap along the anneal, and we're using that to determine the fraction of non-stochastic winds. And what you can see is that the fraction of non-stochastic winds is never that high, right? Already we're pretty far down on this axis. So here you can look at the different curves for whether the coefficients of the path change are chosen uniformly at random or in plus or minus 1. And then also these conditions of whether the true ground state energy subspace. So apparently your best chance of a non-stochastic wind is to take the coefficients uniformly and actually have that condition apply. But it's not so different from not having the condition apply. Now in these other boxes, so this box down here, there's another proposal for taking your non-stochastic Hamiltonian to a stochastic one. The other proposal is to just add matrix elements. So instead of taking the absolute value, you just add in, or subtract, I should say, the matrix elements to make them all stochastic. So we just call this the shift. So two different proposals to associate a non-stochastic Hamiltonian with a stochastic one. And we basically find a similar result, that the fraction of non-stochastic winds stays very small. And then you might ask, well, what if this is just a feature of the spectral gap? What if we can get around this by looking at the overall time to solution in a mode that allows us to proceed faster with a shorter anneal time than a purely adiabatic mode? So that's what this column corresponds to. So here's the de-signed case and the shifted case. And again, we're just kind of always seeing a small fraction. And in fact, it's an even more clear decrease with system size in the TTS case. So we would have liked to see a change with system size here, but we weren't able to access that scaling. But it's kind of what we would expect, that as you go out to large qubit number, this fraction of winds might decay. Okay, so those are the main technical results I wanted to communicate. So now I want to make some higher level remarks that also relate to the perspectives paper that I wrote with Daniel. So, you know, non-stochastic Hamiltonians, I would say, were one of the last great hopes for this original proposal of adiabatic optimization to achieve some kind of drastic speed up. And so I think that there's a bit of a cautionary tale here about equivocating hardness of classical simulation with useful algorithmic enhancement, you know, which is what's going on in quantum supremacy. But of course, non-stochastic interactions could be useful for many things. So they're crucial for universal AQC. They could be used for adiabatic quantum simulation, and they can be used within Hamiltonian error suppression. And since our d-signed Hamiltonians contain multi-spin stochastic interactions, minus XX, minus XXX, etc., the experimental progress on those still has great value. But you know, still the experimental challenges in, so if you like, you know, to borrow Jamie Kerman's term, full static emulation of a vector spin 1/2 qubit, i.e. all possible two local interactions, that's been experimentally challenging. So this led us to conclude in the perspectives paper that diabatic quantum annealing is perhaps the best path forward for near-term optimization in analog systems. So one reason to continue pursuing analog optimization is that if you look at it carefully, the overhead of gate model fault tolerance can easily consume the mild polynomial advantage of algorithms like Grover or amplitude amplification when it comes to a real finite application scale. So the idea of getting a quantum advantage from a fault tolerant gate model computer just because we have some polynomial speedups with these algorithms is not a slam dunk just because we aren't really in the n goes to infinity limit, but we're capped at some finite application scale. And so because of that, you know, we need to explore these alternatives. We can't just say that, that it's all going to be gate model fault tolerance one day, because it's not clear that there's an advantage there. So that's discussed a bit in this work. But I also want to kind of take a step back and say, you know, what should we think about as theorists in this new field of heuristic quantum optimization? So I'm fully excited for the next round of hardware development and benchmarking studies. But as we heard, you know, in say Eleanor's talk, how, you know, part of the idea of heuristics is that you just want to build the thing and try them. So how should theoretical researchers contribute to these heuristics? I think that the connections between DQA and QAOA are an exciting recent development. But you know, we're currently kind of in an era where there's a gold rush of researchers proposing these heuristic methods as fast as they can write the papers. You know, act now to claim your own variational quantum circuit ansatz. So as theorists, I think what we should do is look at the bigger picture and try to address these algorithms that are just popping up over and over in a general way. And so recent work that applied a really general perspective to rule out quantum advantage in extremely noisy devices is this paper that many of you may have seen on the archive. And I think it's admirable in the sense that it takes on a large general class of algorithms. In terms of the specific result, I would say it applies to the extremely noisy regime. And in fact, the classical competing algorithms in this work are sort of directly related to the high temperature simulation results. So you could think of what they're simulating, you know, is so high temperature, so noisy, that you're almost just guessing random strings. But anyway, I like this work because it's very general at addressing these algorithms. Something I just want to point out is that, you know, in this community, we seem to be fixated on using the problem Hamiltonian as a phase separation operator, right? And so maybe that's the right general class of algorithms to address, or maybe we should start thinking outside of that box, right? So here in the context of quantum annealing, I'm thinking that if you trotterize the evolution, you're really just inserting the problem Hamiltonian through this phase separation operator. And, you know, in a way, this is a really simple idea. It's almost the simplest way you could think of plugging the cost function into your quantum algorithm. But if you look at classical algorithms like branch and bound or simulated annealing, they involve these more complex primitives, adaptivity, examining clauses one by one, and so on. So I think it's time for us to evaluate this general idea. That's at least one thought I want to share. And then the very last thing is just that we are looking for postdocs at the University of New Mexico. So we have a bunch of recent new faculty. You may recognize myself, Tamim Milad. We have a bustling center for quantum information and control. Our postdoctoral fellows can work with any of our faculty or pursue their own research interest, and deadline soon, and you could start soon. So contact me if you'd like more information on that. And with that, I'll end. Thank you.
Okay, so I think this was the last talk of the program, and we are only 3 minutes over schedule. So closing is in order, and I have to thank all the speakers and all the co-organizers and who co-hosted also with me the conference. And again, the people in the technicians and the secretaries who have really have gone out of their ways to help us running this marathon conference here. And as usual, at the end of the Adiabatic Quantum Computation Conference, there should be an announcement regarding the location of next year. This announcement cannot be done because of the obviously uncertainty in the situation in the world due to the COVID pandemic. So we don't know where the conference next year will take place. And this was the only announcement that I had to give, service announcement. And I thank you again, everybody. This was a great success, and it was fun for me, and I hope this was fun for you too. Thank you, and see you. Goodbye from Trieste. Bye-bye.
Thank you very much. Goodbye. Goodbye from Cesar. Bye.
Goodbye. Thank you.
Thank you a lot. Bye-bye.
Thanks. Bye.